Please subscribe to support the channel. When we gaze up at the night sky, most stars seem like distant pinpricks of light, silent, eternal, and unchanging. But hidden among those points of brilliance are cosmic titans, stars so powerful and volatile that they redefine what we think we know about the universe. Among these giants, one stands out not just for its brightness, but for the mystery and danger it represents. This star has fascinated astronomers for centuries, and today, it continues to spark curiosity, excitement, and even a little fear. That star is Betelgeuse. Betelgeuse is one of the most iconic and easily recognizable stars in our sky. Located in the constellation Orion, a constellation so famous that almost everyone on Earth has seen it at least once, Betelgeuse sits proudly as one of its defining jewels. This isn't just another anonymous star lost in the sea of light. Betelgeuse is legendary in both scientific circles and cultural history. Its name itself comes from Arabic origins, roughly meaning the armpit of Orion, which is fitting since it marks Orion's shoulder in the sky. The first thing to understand about Betelgeuse is just how prominent it is to the naked eye. Even people who aren't astronomers or sky watchers can often pick it out without knowing what they're looking at. It doesn't require a telescope, binoculars, or special equipment. Betelgeuse is right there, shining brightly, demanding attention. And unlike many stars that twinkle in a cold bluish or white tone, Betelgeuse has a distinctly reddish hue. That red glow is the calling card of a star that is not just bright, but incredibly massive and nearing the final chapters of its life. Historically, civilizations across the globe have noticed Betelgeuse's brilliance. Ancient cultures often connected it to mythologies surrounding Orion the Hunter, while in more recent centuries, astronomers have carefully studied its brightness, color, and changes. For centuries, Betelgeuse has been a celestial beacon, one of those special stars that humanity has kept an eye on, generation after generation. Today, astronomers classify Betelgeuse as the 10th brightest star in the night sky, though its brightness has fluctuated over time, which makes it all the more intriguing. Its prominence is not simply a result of its physical brightness but also its location. Orion is one of the most famous constellations, and Betelgeuse, sitting at Orion's upper left corner, naturally stands out. Whether you're a casual stargazer or a seasoned astronomer, Betelgeuse is a star that refuses to go unnoticed. What makes Betelgeuse especially fascinating is that it's not just another twinkling light, it's a cosmic ticking time bomb. Even though it sits far beyond our solar system, its behavior, structure, and eventual fate are tied to some of the most powerful processes in the universe. It's a star that astronomers watch carefully not only because of what it is now, but because of what it will eventually become, a supernova. But before we get there, we must first appreciate it as it is, one of the most brilliant stars ever to grace our skies. If you've ever stepped outside on a clear winter night in the northern hemisphere, chances are you've seen Orion, one of the most recognizable constellations in the entire sky. Orion is bold, symmetrical, and unlike many faint constellations that require imagination to see, Orion practically leaps out at you. At its center is Orion's belt, 3 bright stars in a perfectly straight line. Above the belt sits a bright, reddish star, that's Betelgeuse. This placement in Orion gives Betelgeuse its reputation as the shoulder of the hunter, and it's one of the easiest stars to find without any equipment whatsoever. What makes Betelgeuse so noticeable isn't just its position, but also its color. While most stars appear white or bluish to the naked eye, Betelgeuse has a distinct orange-red hue. This difference is dramatic when you compare it to Rigel, Orion's other bright star, which shines a crisp, bluish-white. Rigel represents Orion's foot, and together with Betelgeuse, the two stars create a striking visual contrast. Even if you're a complete beginner to stargazing, your eyes can pick out this difference almost instantly. The red glow of Betelgeuse sets it apart from most of the other bright stars in the sky, which is why it's often one of the first stars that astronomy teachers or guides point out to newcomers. In fact, Betelgeuse's reddish light has been recorded by cultures around the world for millennia. Ancient astronomers in China, the Middle East, and Europe all noted its color and brightness. Its red tint was often associated with omens, war, or passion because of the cultural symbolism of the color red. Some Native American traditions even referred to Betelgeuse as a fiery star, connecting it with warmth and energy. That human fascination with its reddish hue is part of why Betelgeuse has remained in our collective imagination for so long. If you want to find Betelgeuse yourself, The trick is simple. First, locate Orion's belt, those three bright stars in a straight, diagonal line in the middle of the constellation. From there, look upward and slightly left, and you'll see Betelgeuse shining brightly, its red-orange glow unmistakable. The star sits like a jewel at Orion's shoulder, always keeping its place in the sky as the hunter's raised arm. Because Orion is one of the most prominent constellations across the globe, visible in both the northern and southern hemispheres at different times of the year, Betelgeuse is also one of the most universally recognizable stars in human history. The visibility of Betelgeuse also changes subtly depending on the season and where you are on Earth. In the northern hemisphere, Orion dominates the winter skies. On cold December or January nights, Betelgeuse climbs high above the horizon, glowing steadily as one of the jewels of winter stargazing. In the southern hemisphere, Orion is seen during the summer months, but the pattern of the constellation flips upside down. Down there, Betelgeuse appears at Orion's lower shoulder instead of the upper, yet it remains just as bright and obvious to the naked eye. No matter where you are on Earth, when Orion is up, Betelgeuse is practically impossible to miss. The other reason Betelgeuse is so easy to spot is its sheer brightness. Astronomers measure the brightness of stars in terms of apparent magnitude, with lower numbers meaning brighter stars. Betelgeuse usually hovers around magnitude 0.4, though its variability can make it brighter or dimmer. For context, the faintest stars visible to the naked eye under dark skies are around magnitude 6. That means Betelgeuse is roughly 100 times brighter than the faintest star most people can see. Even in light-polluted city skies, where only the brightest stars shine through, Betelgeuse usually stands tall. There's also something special about the way Betelgeuse twinkles. All stars twinkle due to Earth's atmosphere, but Betelgeuse, because of its red light, tends to shimmer in a way that can almost look like it's pulsing between shades of red, orange, and yellow. That subtle flickering adds to its mystique. Sometimes, people mistake this twinkling for the star being unstable or about to explode, and while Betelgeuse is indeed nearing the end of its life, the nightly twinkling is simply an atmospheric effect, not a sign of imminent danger. For casual stargazers, Betelgeuse is often their introduction to the idea that not all stars are the same. Its visibility makes it a teaching tool, a starting point for explaining the diversity of stars. When someone notices the difference between Betelgeuse and Rigel, they're actually observing the difference between stellar temperatures. Rigel, with its blue-white glow, is extremely hot, around 12,000 Kelvin on its surface. Betelgeuse, with its reddish color, is cooler at about 3,500 Kelvin. And yet, despite being cooler, Betelgeuse is vastly larger and more luminous overall because of its enormous size. This simple visual contrast that anyone can see with their own eyes is a doorway into the vast complexities of stellar physics. Another remarkable aspect of Betelgeuse's visibility is how it interacts with mythology and storytelling. For thousands of years, its place in Orion has made it a reference point in the night sky. Sailors once used Orion's bright stars, including Betelgeuse, for navigation. Farmers used its seasonal appearance to track the time of year. Storytellers across different cultures incorporated its red light into legends. In a way, Betelgeuse has been guiding humanity not just scientifically but also culturally, shining down on us as both a beacon and a mystery. And so, Betelgeuse's visibility is more than just an astronomical fact, it's a human experience. It is one of the rare stars that bridges the gap between science and culture, between what we can calculate with instruments and what we can simply admire with our eyes. Every time you see that red star twinkling above Orion's belt, you're witnessing not just a bright star, but a colossal giant nearing the end of its life, a cosmic event in waiting, written across the canvas of the sky for all of us to see. When we look up at Betelgeuse in the night sky, it might appear to us as nothing more than a bright, reddish point of light. But in reality, this single dot is a monstrous giant, one of the largest stars ever observed. Betelgeuse belongs to a rare class of stars known as red supergiants, the bloated, dying titans of the stellar world. And when we say it is big, that's an understatement so profound that our human minds struggle to even comprehend the scale. Let's start with a comparison that's easier to grasp. Our own Sun, though massive to us, is just an average, run-of-the-mill star. Its diameter is about 1.4 million kilometers, big enough that over 1 million Earths could fit inside it. Now, Take that mental image and multiply it almost 1,000 times. That's Betelgeuse. Its diameter is estimated to be around 1.2 billion kilometers, which makes it nearly 1,000 times larger than the Sun. Imagine the Sun as a coin in your hand. Betelgeuse, by comparison, would be a sphere the size of a large stadium. This scale becomes even more staggering when you place Betelgeuse inside our solar system. If you were to hypothetically pick up Betelgeuse and replace the Sun with it, its swollen atmosphere wouldn't just engulf Mercury and Venus. It wouldn't even stop at Earth or Mars. Betelgeuse is so immense that its surface would stretch all the way past the orbit of Jupiter. Think about that, every single planet we know, including the gas giant Saturn, Uranus, and Neptune, would be swallowed by Betelgeuse if it sat at the center of our solar system. The Earth, with all its oceans, mountains, and human history, would simply be a speck buried deep inside the fiery outer layers of this colossal star. This is why astronomers often call Betelgeuse a stellar monster. It redefines what we think of as large. And what makes this even more fascinating is that despite its size, Betelgeuse is not dense in the way we might expect. Because red supergiants expand as they near the end of their lives, their outer layers become incredibly diffuse. If you could somehow scoop up a handful of Betelgeuse's outer atmosphere, it would be thinner than the air we breathe here on Earth. That's right, something that looks so overwhelming and solid from our perspective is, in truth, a giant puffball of hot, tenuous gas. This bloated nature is a direct result of Betelgeuse's stage in stellar evolution. Stars spend most of their lives in a stable phase, fusing hydrogen into helium in their cores. Our Sun is in this phase now and will remain stable for billions of years. But for a star as massive as Betelgeuse, life moves much faster. After exhausting its hydrogen, Betelgeuse began burning heavier elements, causing its core to shrink and its outer layers to balloon outward. This expansion transforms a once compact and hot blue star into the swollen red supergiant we see today. The larger the star, the more extreme the expansion. Betelgeuse is one of the most extreme cases we've ever measured. To illustrate just how vast this star is, astronomers sometimes compare its size to everyday experiences. For instance, if Betelgeuse were placed at the center of our solar system and Earth somehow survived inside it, the distance from Earth to the surface of Betelgeuse would take hundreds of years to travel by commercial airplane. That's not hundreds of flights, that's hundreds of years flying non-stop at 900 kilometers per hour. The sheer immensity is incomprehensible. Another way to imagine it, if Betelgeuse were a balloon, and you could scale it down so that our Sun was the size of a small marble, Betelgeuse would be a balloon nearly the size of a city block. The comparison is so extreme that it doesn't just make Betelgeuse fascinating, it makes it unsettling. The sheer enormity of this star is almost alien to us. And here's another mind-bending fact. Despite being so massive, Betelgeuse is not the largest star in the universe. Astronomers have identified other red supergiants, like UY Scuti and VY Canis Majoris, that are even bigger. But Betelgeuse holds a special place because of its proximity and visibility. It is one of the few stars of this colossal size that we can actually study in detail, which makes it a window into the lives of the universe's most extreme stars. Betelgeuse's size is not just a curiosity, it's also a warning. A star cannot sustain itself in such a bloated state forever. The very fact that Betelgeuse is so large tells astronomers that it is nearing the end of its life. Its vast, unstable outer layers are a sign that it has entered its final act. While our Sun will remain calm for billions of years to come, Betelgeuse is living fast and dying young, burning through its fuel at a furious rate. And yet, even in its instability, its size gives us a breathtaking spectacle. Imagine a star so immense that you could point to it in the night sky with your bare eyes and know that glowing red is a giant so vast it could swallow our solar system whole. The human mind may struggle to comprehend it, but Betelgeuse is a living example of how the universe stretches far beyond our familiar scales. When we talk about distances in space, the numbers quickly become so vast that they defy ordinary understanding. Even the distance from the Earth to the Sun, about 150 million kilometers, is already hard to imagine. Yet, that's just a single step in the vast cosmic ocean. Now, when we speak about stars like Betelgeuse, we leave behind kilometers entirely and switch to a new unit, the light year. 1 light year is the distance that light, the fastest thing in the universe, can travel in 1 year, nearly 9.46 trillion kilometers. Betelgeuse is approximately 640 light-years away from Earth. At first glance, that sounds unimaginably far. If you could somehow board the fastest spacecraft ever built by humans, traveling at tens of thousands of kilometers per hour, it would take millions of years just to get there. To us, stuck on our small planet, 640 light-years feels like a number that puts Betelgeuse completely out of reach. But here's the twist. On the cosmic scale, 640 light-years is shockingly close. Our Milky Way galaxy alone is about 100,000 light-years wide. Compared to that, Betelgeuse is practically our neighbor, located well within our local stellar neighborhood. It is one of the nearest red supergiants to Earth, which is part of the reason astronomers are so fascinated by it. Most stars of this type are far too distant to study in such detail, but Betelgeuse's relative closeness gives us a front-row seat to a stellar drama that is unfolding in real time. Another way to think about this, if the Milky Way was scaled down to the size of North America, Betelgeuse would be like living just one town over, close enough to see clearly, yet far enough that we're not in immediate danger from whatever happens in that town. That's exactly how it is with Betelgeuse. It is close enough that its light shines brightly into our night sky, and close enough that we will one day witness its spectacular death as a supernova, but far enough that the destructive effects of that explosion won't reach us. It's also worth remembering that when we look at Betelgeuse, we are not seeing it as it is today. We're seeing it as it was 640 years ago, because that's how long it takes for light to travel from Betelgeuse to Earth. That means the reddish glow you see in Orion's shoulder tonight actually left the star around the year 1385, during the Middle Ages. The star you're looking at now may already be drastically different. It could have expanded, changed brightness, or even exploded, but we won't know until the light of those changes arrives on Earth centuries later. In this sense, stargazing is also time travel. Every time we look up, we're looking back into history, and Betelgeuse provides one of the most dramatic examples of that concept. This delay also adds to the suspense around Betelgeuse's future. We know it's nearing the end of its life, but because of the light travel time, it's possible that it has already gone supernova, and we just haven't seen it yet. If Betelgeuse exploded, say, 500 years ago, the light of that event is still on its way to us, racing across interstellar space, and when it arrives, the star will suddenly brighten in our skies in a display unlike anything modern humanity has ever seen. This thought alone makes Betelgeuse's distance all the more intriguing. It creates a cosmic ticking clock that none of us can set. Astronomers have worked hard to refine the measurement of Betelgeuse's distance. For many years, estimates ranged from 500 to 700 light-years, since measuring such distances isn't easy. Unlike nearby stars whose positions shift slightly against the background when observed from different points in Earth's orbit, a method called parallax, Betelgeuse is so far and so large that precise measurements are difficult. Only with advanced telescopes and instruments like the European Space Agency's Hipparcos and Gaia missions have we been able to narrow the estimate to around 640 light-years. Even now, there's still some uncertainty, a reminder of just how challenging it is to pin down the properties of stars beyond our immediate solar neighborhood. To put 640 light-years into more tangible terms, imagine that light leaving Betelgeuse tonight will still be traveling across space when our descendants are 640 years older. Entire civilizations could rise and fall in the time it takes for a single photon to bridge the gap between Betelgeuse and Earth. That's why astronomers often speak of distances in space with awe, not because we can't calculate them, but because they stretch the limits of human comprehension. Despite its distance, Betelgeuse is one of the few stars that can actually be resolved as more than just a point of light. Thanks to powerful observatories like the Very Large Telescope in Chile, astronomers have been able to create detailed images of Betelgeuse's surface, showing bright and dark patches caused by massive convective cells of gas rising and falling within its outer layers. This is extraordinary, because nearly every other star we see in the sky, no matter how close or bright, appears as nothing more than a tiny, even through a telescope. Betelgeuse is so huge and so close that we can literally begin to map its surface, a cosmic privilege we don't have with most other stars. So while 640 light-years might sound distant, it is precisely this balance, close enough to study, far enough to remain safe, that makes Betelgeuse one of the most important stars in the heavens. It is a reminder that even though the universe is unimaginably vast, sometimes we are fortunate enough to have front-row seats to its most dramatic stories. Betelgeuse's proximity ensures that when the day comes for it to explode, Earth will have the rare opportunity to witness one of the most spectacular light shows in the history of our species. Up to this point, we've explored Betelgeuse as one of the brightest and most recognizable stars in the sky, admired its sheer size, and marveled at its relative closeness to Earth. But the real intrigue of Betelgeuse lies not only in what it is now, but in what it is becoming. Unlike our Sun, which is stable and steady in its middle-aged life, Betelgeuse is anything but calm. It is a star in turmoil, a giant in the throes of old age, nearing the end of its cosmic journey. To understand Betelgeuse is to recognize that it is unstable, a star on the verge of an inevitable, spectacular collapse. Stars are not eternal. They are born, they live, and eventually, they die. Their lifespans depend largely on their mass. Smaller stars, like our Sun, can live for billions of years, slowly burning hydrogen fuel in a steady, balanced way. But stars like Betelgeuse, with masses estimated to be 15 to 20 times that of the Sun, live fast and die young. They burn through their nuclear fuel at an astonishing rate, like a roaring bonfire compared to a candle flame. This furious pace means that while our Sun is expected to last about 10 billion years in total, Betelgeuse's lifespan is measured in only about 10 million years. That's just a blink of an eye in cosmic terms. Betelgeuse is currently in the red supergiant phase, one of the final stages of a massive star's life cycle. This phase itself is a sign of instability. The star has already burned through the hydrogen in its core, which sustained it during its youth. Without hydrogen fusion in the center, the core shrank under gravity, heating up and igniting new rounds of fusion involving heavier elements like helium, carbon, and oxygen. Each new fuel source burns faster and less efficiently than the last, causing the core to contract further and the outer layers to swell enormously. This cycle of burning and expansion is not stable, it's chaotic. Betelgeuse is essentially staggering toward its end, struggling to maintain balance while gravity pulls inward and nuclear fusion pushes outward. This tension makes Betelgeuse a restless, unpredictable star. Its outer atmosphere is turbulent, with enormous convective cells, essentially gigantic bubbles of gas, rising and falling across its surface. These convective cells are so vast that a single one could encompass the orbit of Earth. They churn and boil, creating dramatic shifts in brightness and temperature across the star's surface. The result is a star that never looks the same from one moment to the next, a star whose very structure is in constant flux. Another aspect of Betelgeuse's instability is the loss of mass. The star is shedding material into space at an incredible rate, spewing out gas and dust into its surrounding environment. Over time, Betelgeuse has surrounded itself with a vast cloud of ejected material, a sort of cosmic shroud. This mass loss is a direct symptom of its instability, as its bloated outer layers are only loosely bound by gravity and can be blown away by powerful stellar winds. Eventually, this expelled material will enrich the interstellar medium with heavy elements, but for now, it is part of the dramatic unraveling of a dying giant. From our perspective on Earth, we can actually observe signs of this instability. Unlike most stars, which shine with steady brightness, Betelgeuse flickers and changes. Sometimes it grows brighter, sometimes dimmer, as its outer layers shift and its convective activity changes the amount of light reaching us. This variability has fascinated astronomers for centuries, because it's not just a trivial flicker, it's the outward expression of deep internal chaos. This instability also raises the question everyone wants answered: when will Betelgeuse finally explode? That's the heart of its story. Because the star is in such an advanced stage of evolution, we know the end is coming. It could happen tomorrow, or it could take another 100,000 years. On human timescales, that uncertainty is frustrating. On cosmic timescales, though, it means Betelgeuse is living on borrowed time. We just happen to exist during the rare window in history when a massive star in our cosmic backyard is visibly approaching its finale. To put it in perspective, if our Sun is like a calm middle-aged person with centuries left to live, Betelgeuse is like a giant whose body is failing, lurching from one crisis to the next, with the inevitability of death looming ever closer. Its instability is not a flaw but a natural step in the life cycle of massive stars. This is what they do: shine brightly, live briefly, and die in a blaze of unimaginable energy. And this is precisely why Betelgeuse has captivated both scientists and the public alike. Every wobble in its brightness, every strange event in its outer atmosphere, spark speculation that the end might be imminent. We watch it not just as a star but as a cosmic drama, a celestial countdown whose exact moment remains hidden from us. The instability of Betelgeuse is the reason it is both dangerous and fascinating. It is a reminder that even the brightest stars are mortal, and that in the universe, change is the only constant. One of the most striking features of Betelgeuse, and one that makes it endlessly fascinating to astronomers and casual stargazers alike, is that it doesn't shine with a constant, steady brightness like most stars in the sky. Instead, it is what scientists call a variable star, a star that naturally brightens and dims over time. This variability is not a small, subtle effect that requires sophisticated instruments to detect. In fact, Betelgeuse is one of the few stars whose changes in brightness are noticeable to the naked eye over months or years. It is almost as though Betelgeuse breathes, pulsing in and out, glowing stronger and then weaker in a rhythm set by the chaos within its own body. Astronomers have been documenting this variability for centuries. Betelgeuse usually shines as one of the top 10 brightest stars in the night sky, with a typical apparent magnitude around 0.4. But over time, it can fluctuate dramatically, sometimes brightening to magnitude 0.0, making it nearly as bright as Rigel, and at other times fading to magnitude 1.3 or dimmer, dropping it out of the top 20 brightest stars. For anyone paying attention to the night sky over years, this is obvious. The red shoulder of Orion seems to change personality, sometimes demanding attention, other times withdrawing into the background. The cause of this variability lies in the physics of Betelgeuse's unstable outer layers. Like many red supergiants, Betelgeuse undergoes pulsations, expansions and contractions of its outer atmosphere. These pulsations are driven by the complex processes of nuclear fusion in its core and the convective activity in its vast outer shell. As the star expands, its surface cools slightly, and it grows dimmer. As it contracts, the surface heats up again, and the star grows brighter. These cycles of expansion and contraction can last for months or even years, creating the noticeable changes in brightness we see from Earth. What makes Betelgeuse particularly intriguing is that it doesn't follow just one simple rhythm. Instead, astronomers have detected multiple overlapping cycles of variability. The most well-known cycle is around 400 days, during which Betelgeuse brightens and dims fairly predictably. But on top of that, there are longer-term cycles spanning several years, and even irregular fluctuations that don't fit neatly into any single pattern. It's as though Betelgeuse is beating not just one drum, but an entire chaotic symphony of rhythms. And that's not surprising, given the nature of its outer layers. Betelgeuse's surface is dominated by gigantic convective cells, massive bubbles of hot gas rising and falling, each one larger than the entire orbit of Earth. These cells can cause one side of the star to brighten while another side dims. From our vantage point on Earth, the result is irregular flickering, as if the star itself is alive and restless. Observations using advanced telescopes have even allowed us to image Betelgeuse's surface, showing these bright and dark patches shifting over time, providing visual confirmation of the variability we see with our eyes. For astronomers, this variability is not just an oddity but a crucial clue to understanding what's happening inside Betelgeuse. By tracking how its brightness changes, scientists can infer details about its internal structure, its pulsations, and the processes driving its instability. In many ways, the variability of Betelgeuse is like a heartbeat, a signal that reveals the star's current state of health and how close it may be to its final collapse. For casual observers, though, the variability has an almost mystical quality. Imagine watching Orion each winter for decades and noticing that Betelgeuse seems a little different from year to year. Sometimes it dominates Orion's shoulder, burning brightly against the night sky. Other times, it fades, and Rigel or even Bellatrix outshines it. To ancient skywatchers, these changes must have seemed like signs or omens, proof that the heavens themselves were alive and unpredictable. Even today, in an age of telescopes and satellites, there's something awe-inspiring about being able to see such variability with nothing more than your eyes. This variability also plays into the suspense around Betelgeuse's ultimate fate. Because its brightness can change so dramatically, any major dimming event tends to set off speculation. Is this it? Is Betelgeuse about to explode? And that speculation reached a fever pitch in late 2019 and early 2020, when Betelgeuse underwent the most dramatic dimming ever recorded in modern history, the so-called Great Dimming, which we'll explore in detail later. That event showed just how closely people are watching Betelgeuse and how much its variability fuels both scientific investigation and public imagination. But even without such extraordinary events, Betelgeuse's normal variability is itself a wonder of the universe. It is a reminder that stars are not static points of light but dynamic, living systems undergoing constant change. Betelgeuse doesn't just sit quietly in the sky. It pulses, breathes, and transforms before our very eyes, putting on a cosmic show that connects us directly to the inner workings of a dying giant. In the long history of humanity's fascination with Betelgeuse, few events have captured both scientific and public attention quite like what unfolded between late 2019 and early 2020. Astronomers and skywatchers around the globe noticed something strange happening to Orion's red shoulder. Betelgeuse, normally one of the brightest stars in the sky, began to dim, and not just by a little. Over the span of a few months, its brightness plummeted to levels unseen in centuries. This unprecedented change became known as the Great Dimming, and for a while, it set the world buzzing with one tantalizing question: was Betelgeuse about to explode? To put the event into perspective, Betelgeuse usually hovers near the top 10 brightest stars in the night sky. But during the Great Dimming, its light output dropped by nearly 2/3, falling from its usual magnitude of around 0.4 to about 1.6. This wasn't just a slight flicker, it was dramatic enough that even casual observers who didn't normally track stars could notice it with the naked eye. For thousands of years, Betelgeuse had been a dominant presence in Orion, but suddenly it looked faint, almost ghostly, as though the giant star were visibly fading away before our eyes. News spread quickly, not just in academic circles but in mainstream media. Headlines proclaimed that Betelgeuse could be on the verge of going supernova. Scientists explained that while such an explosion was inevitable, the timing was uncertain. It could happen tomorrow, or it could happen tens of thousands of years in the future. Still, the sheer oddity of Betelgeuse dimming so drastically gave people a sense of urgency. Social media lit up with speculation, memes, and excitement. For the first time in modern memory, ordinary people were watching a star with the expectation that it might die spectacularly at any moment. So what exactly caused this dramatic dimming? At first, no one knew for sure. Betelgeuse is a variable star, and fluctuations in brightness are normal for it, but this event was far beyond the usual pattern. One hypothesis was that massive convective activity within Betelgeuse, those huge bubbles of plasma rising and falling, had temporarily shifted, causing one hemisphere of the star to dim. Another idea was that the star might be entering its final pre-supernova throes, with its core processes destabilizing and leading to observable changes on its surface. For months, astronomers around the world focused their instruments on Betelgeuse, determined to solve the mystery. The dimming was so pronounced that it could be observed with everything from large professional telescopes to small backyard setups. The collective attention of both professional scientists and amateur skywatchers made Betelgeuse one of the most scrutinized stars in the universe during that time. Eventually, the evidence began to converge on a fascinating explanation: dust. Observations from the European Southern Observatory's Very Large Telescope in Chile provided detailed images of Betelgeuse during the dimming, showing that part of the star's surface appeared obscured. What seems to have happened is that Betelgeuse ejected a massive amount of material, a giant plume of gas. As this hot gas traveled outward and cooled, it condensed into dust grains, forming a localized dust cloud that partially blocked the star's light from reaching Earth. In other words, Betelgeuse essentially sneezed, and that cosmic sneeze created a veil of dust that made it look dimmer to us. This explanation fit the observations beautifully. Betelgeuse, as a red supergiant, is already prone to shedding its outer layers, and mass ejections like this are not uncommon for dying stars. What was unusual was the sheer scale of the event and how visible its effects were from Earth. The dust cloud not only explained the dimming but also reinforced the fact that Betelgeuse is in an unstable, late stage of life. By mid-2020, Betelgeuse began to brighten again, returning to its normal level of visibility. The Great Dimming, though temporary, left a permanent mark on both the scientific community and the public imagination. For astronomers, it was an invaluable opportunity to study a red supergiant in action, offering real-time data about mass loss, surface activity, and the complex interplay of processes in such a massive star. For the public, it was a reminder that the universe is alive and changing, and that we are privileged to witness events that would have seemed like omens to ancient peoples. The Great Dimming also served as a rehearsal of sorts for the eventual supernova. When Betelgeuse does explode, the changes will be unmistakable and dramatic. The dimming gave scientists and the public alike a taste of what it feels like to watch Betelgeuse behaving unpredictably, stirring both anticipation and awe. It showed us that stars are not eternal points of light but dynamic, evolving titans whose stories are still unfolding before our eyes. In the end, Betelgeuse's great dimming wasn't the herald of its final collapse, but it was a spectacular reminder of its instability and a testament to its status as one of the most closely watched stars in the universe. It's almost poetic. The star gave us a preview of its ability to astonish, as though it were teasing us with the promise of an even greater spectacle still to come. When the Great Dimming first began in late 2019, astronomers and the general public were swept up in speculation. Was Betelgeuse about to go supernova? Was this the long-awaited signal of the star's imminent collapse? For months, the question loomed large, but as more observations rolled in, the pieces of the puzzle began to fit together. The mystery dimming wasn't caused by the star's core running out of fuel. It wasn't the beginning of the end, at least not yet. Instead, the culprit was something equally fascinating and revealing: a dust cloud, created from material ejected directly from Betelgeuse's surface. To understand this explanation, it helps to recall just how unstable Betelgeuse really is. The star's outer layers are turbulent and tenuous, more like a frothing ocean than a solid surface. Massive convection cells, each one larger than the orbit of Earth, churn and bubble, carrying hot plasma upward and cooler material downward. These violent movements can sometimes throw out enormous quantities of gas into space. Under normal conditions, such gas disperses harmlessly, blending into the interstellar medium. But in the case of the Great Dimming, the gas ejected was so substantial that it cooled rapidly and condensed into solid particles, dust grains, forming an enormous veil in front of the star. Think of it as Betelgeuse coughing or sneezing, expelling part of itself into the surrounding space. That expelled material then floated in front of the star along our line of sight, acting like a cosmic curtain that blocked a significant fraction of its light. To us on Earth, it looked like the star itself had dimmed, but in reality, much of its brilliance was simply hidden behind this temporary dust cloud. The European Southern Observatory's Very Large Telescope, VLT, played a key role in solving the mystery. Using high-resolution imaging, astronomers were able to capture actual pictures of Betelgeuse's surface before, during, and after the dimming. These images revealed that one portion of the star had grown significantly darker than the rest. It wasn't a uniform dimming across the whole star, it was localized, as though something were covering part of it. This strongly supported the idea that the dimming was caused not by a change inside the star itself, but by something blocking its light. Subsequent infrared observations added further evidence. Dust emits infrared radiation, and instruments sensitive to those wavelengths detected an excess coming from the region around Betelgeuse. This indicated that the ejected material had indeed cooled and condensed into dust particles large enough to scatter and absorb visible light. The dust wasn't just a thin haze, it was dense and substantial enough to reduce the star's visible brightness by more than half. This discovery was remarkable not only because it explained the Great Dimming, but also because it gave astronomers an unprecedented look at how massive stars lose material in their final phases. Mass loss is one of the defining features of a red supergiant's life, and Betelgeuse is shedding its outer layers at an astonishing rate, the equivalent of losing Earth's mass every year. The 2019 to 2020 event was a particularly dramatic example, essentially allowing us to witness stellar mass loss in real time. The dust cloud explanation also carried a profound reassurance. Betelgeuse was not in the process of collapsing into a supernova, at least, not yet. Its core was still stable enough to continue burning heavier elements in succession. The dimming event was more like a dramatic hiccup, a surface-level convulsion rather than a terminal collapse. That doesn't mean Betelgeuse's fate has changed. It is still destined to end in a supernova. But the Great Dimming was a reminder that giant stars like Betelgeuse are messy, unpredictable, and prone to spectacular outbursts long before the final explosion arrives. Perhaps the most awe-inspiring part of the story is how this expelled dust, which once hid Betelgeuse from us, will one day become part of the cycle of cosmic creation. The material ejected during the Great Dimming, carbon, oxygen, silicon, and other heavy elements, will drift into the interstellar medium, enriching the space around Orion. Over millions of years, that dust could contribute to the formation of new stars, new planets, and perhaps even the building blocks of life. In other words, Betelgeuse's sneeze wasn't just a spectacle for us to marvel at. It was also part of the star's ongoing contribution to the universe. By mid-2020, Betelgeuse brightened again as the dust cloud dissipated and the line of sight cleared. But the event left a lasting impact on astronomy. It reminded us of how dynamic and alive the universe really is. We didn't just read about a star dimming in textbooks, we lived through it. Millions of people around the world stepped outside, looked up at Orion, and noticed with their own eyes that one of the brightest stars in the sky had grown pale. It was a rare moment when humanity collectively experienced the instability of a dying star in real time. So while the great dimming didn't herald the final collapse of Betelgeuse, it was far from meaningless. It showed us how red supergiants live and die, how they expel their outer layers into the cosmos, and how even a single star, hundreds of light years away, can remind us that the universe is full of surprises. When we look up at the night sky, it's tempting to think of stars as eternal, unchanging beacons. For much of human history, people believed exactly that stars were fixed, eternal, and immune to the passage of time. But modern astronomy has revealed a deeper, more dramatic truth. Stars live, they evolve, and they eventually die. And not all stars live the same kinds of lives. Some, like our Sun, enjoy long, steady existences measured in billions of years. Others, like Betelgeuse, burn far hotter, live far faster, and die far sooner. In fact, the story of Betelgeuse can't be understood without comparing it to the lifespan of stars like our own Sun. The lifespan of a star depends primarily on one factor: mass. The more massive a star is, the more fuel it has, but paradoxically, the shorter its life. This is because massive stars like Betelgeuse burn through their fuel at an extraordinarily rapid pace. Their cores operate at much higher pressures and temperatures, driving nuclear fusion at furious rates. Imagine two lamps, one burning with a gentle flame, the other roaring with an inferno. The small flame might last the whole night, but the raging inferno will consume its fuel much more quickly, even if it started with more fuel to begin with. Our Sun is a G-type main sequence star, a fairly average star by cosmic standards. It's about 4.6 billion years old right now and is expected to live for around 10 billion years before exhausting the hydrogen in its core. That's a long, stable existence. During this time, life has had the opportunity to arise and evolve on Earth. Civilizations have come and gone, and entire epochs of planetary history have unfolded. The Sun's relatively slow and steady burning makes it a perfect cradle for life as we know it. Betelgeuse, by contrast, was never destined for such longevity. It started its life as a star with 15 to 20 times the mass of the Sun, and that enormous mass has sealed its fate from the very beginning. Instead of billions of years, Betelgeuse's entire lifespan will last only 8 to 10 million years. That might sound like a lot of time to us, but in cosmic terms, it's the blink of an eye. To put it in perspective, dinosaurs were still roaming Earth when Betelgeuse first ignited as a young star. While our Sun still has nearly 5 billion years of life left, Betelgeuse is already nearing the end of its journey after just a few million years. Why the difference? It all comes down to energy consumption. In its core, Betelgeuse initially fused hydrogen into helium, just like the Sun is doing now. But because Betelgeuse is so much more massive, the temperatures and pressures at its core were vastly higher. This meant hydrogen fusion happened at an accelerated rate, depleting its reserves much faster. After just a few million years, Betelgeuse exhausted the hydrogen in its core, forcing it to transition to fusing helium, then heavier elements like carbon, neon, oxygen, and silicon. Each successive stage of fusion is shorter than the last, and today Betelgeuse is thought to be burning through these heavy elements, rapidly approaching the end of the line. Meanwhile, the Sun is still leisurely burning hydrogen, with no rush to move on. It's like comparing a marathon runner pacing themselves for endurance versus a sprinter going full throttle from the start. Betelgeuse is that cosmic sprinter, destined for glory but not for longevity. This contrast in stellar lifespans has profound consequences for the universe. Stars like the Sun live long enough to create stable planetary systems where life can develop and evolve over billions of years. But stars like Betelgeuse, though short-lived, play an equally vital role. They enrich the cosmos with heavy elements when they explode as supernovae. Without massive stars, there would be no iron in our blood, no oxygen in our atmosphere, and no silicon in the rocks beneath our feet. In a sense, stars like Betelgeuse sacrifice longevity for intensity, burning brightly and dying young, but leaving behind the ingredients necessary for future stars and planets. The brevity of Betelgeuse's lifespan also gives us a sense of urgency. Because it evolves so quickly compared to stars like the Sun, astronomers know it's already in its final act. The fact that it's only a few million years old but already unstable and nearing supernova reminds us that we're witnessing a rare and fleeting stage of stellar evolution. For astronomers, Betelgeuse is like a rare patient in a cosmic hospital, one who is in critical condition, offering scientists invaluable insights into the processes of stellar death. It's also humbling to realize just how different Betelgeuse's story is from our Sun's. While the Sun will eventually swell into a red giant and then quietly fade into a white dwarf, Betelgeuse will go out in a violent, spectacular supernova, lighting up the galaxy. Both stars are playing their roles, but on vastly different timescales and with vastly different endings. In short, Betelgeuse's lifespan reminds us of the universe's diversity. Some stars are gentle and enduring, like our Sun. Others are titanic and short-lived, like Betelgeuse. Together, they weave the cosmic cycle of creation and destruction, life and death. By comparing the lives of these two types of stars, we not only understand Betelgeuse better but also gain perspective on the delicate balance that makes our existence possible. At the heart of Betelgeuse lies the true drama of its existence, a furnace where the laws of physics are pushed to their limits and where the fate of the star itself is decided. To understand why Betelgeuse is nearing the end of its life, we need to look beyond the glowing red surface and peer deep into its core processes. These processes not only determine how the star shines today, but also dictate how and when it will ultimately meet its explosive end. Like all stars, Betelgeuse began its life by fusing hydrogen into helium in its core. This is the most efficient and longest-lasting phase of a star's life, known as the main sequence. For a star like our Sun, this stage lasts billions of years. But for Betelgeuse, with more than 15 times the Sun's mass, hydrogen fusion was a relatively brief chapter, lasting only a few million years. Once that hydrogen fuel ran out, the star's core could no longer produce the pressure needed to counteract gravity, and the structure of the star changed dramatically. When hydrogen was depleted in its core, Betelgeuse moved on to fusing helium into carbon and oxygen. This marked its transition into a red supergiant, causing its outer layers to swell enormously. At this stage, Betelgeuse became the enormous, bloated star we see today, with a size so vast it would engulf the orbits of Mercury, Venus, Earth, Mars, and even Jupiter if it sat in place of our Sun. But the story didn't stop there. Helium fusion, while powerful, is also much shorter-lived than hydrogen fusion. And when helium ran out, Betelgeuse entered a frantic cycle of burning heavier and heavier elements in its core. Today, Betelgeuse is thought to be in the advanced stages of this process. Inside its core, layers of fusion are occurring like an onion, with different elements burning in concentric shells. Hydrogen still fuses in the outermost shells, while deeper layers burn helium, carbon, neon, oxygen, and even silicon. Each layer is shorter-lived than the one before it, and each step brings Betelgeuse closer to its inevitable collapse. This sequence of fusion has a clear pattern. As the star burns through heavier elements, the timescales shrink dramatically. For example, a hydrogen burning can last millions of years. A helium burning may last hundreds of thousands of years. A carbon burning lasts only a few hundred years. A neon burning might persist for just a single year. An oxygen burning can be as short as several months. A silicon burning, the final stage, lasts only a few days. Silicon fusion produces iron, and that's where the process hits a dead end. Unlike lighter elements, iron cannot release energy through fusion. Fusing iron actually consumes energy instead of producing it, which means the star can no longer sustain the outward pressure needed to balance the inward pull of gravity. At that moment, the delicate equilibrium that has kept Betelgeuse alive for millions of years will collapse catastrophically. This frantic race through elements is what makes Betelgeuse so unstable today. Astronomers don't know exactly which stage Betelgeuse is currently in, whether it's burning carbon, oxygen, or even silicon, but the fact that it has left behind the relatively stable hydrogen and helium burning phases tells us one thing for certain: the star is living on borrowed time. Whether it has 100,000 years left or only decades, Betelgeuse is definitively in the late stages of stellar evolution. The processes in Betelgeuse's core are not just abstract science, they are cosmic alchemy at work. In these nuclear forges, the elements that make life possible are being created. Every atom of oxygen you breathe, every molecule of calcium in your bones, every speck of iron in your blood, all of these elements were once forged in the heart of a massive star like Betelgeuse. This makes Betelgeuse's core not only the stage for its dramatic death, but also a birthplace of the materials that will one day seed future stars, planets, and even life. What's remarkable about Betelgeuse's core processes is how they highlight the star's instability. The outer layers of Betelgeuse respond to the changes deep inside, swelling and contracting, pulsing in brightness, and sometimes even ejecting matter into space, like we saw during the Great Dimming. These surface phenomena are directly tied to the frantic, short-lived fusion processes occurring at its core. In a way, Betelgeuse is like a candle that has burned brightly for a short time and is now flickering, sputtering as it consumes the last of its wax. The flickers may not tell us the exact moment when it will go out, but they remind us that the end is near. For Betelgeuse, those flickers are the rapid burning of heavier elements, a signpost on the road to one of the most spectacular events the universe has to offer, a supernova. For all its grandeur and brilliance, Betelgeuse's story is destined to end in violence. Every stage of its existence, the furious hydrogen burning of its youth, the helium fusion that inflated it into a swollen red supergiant, and the frantic race through heavier and heavier elements, has been leading toward one inevitable fate. Betelgeuse will not fade gently into the night as our sun will. Instead, it is fated for one of the most dramatic finales the cosmos has to offer, a supernova explosion. Supernovae are among the most powerful events in the universe, rivaling the brightness of entire galaxies for brief periods of time. They are not common. In a galaxy like the Milky Way, they occur perhaps once or twice per century, but when they do happen, they are unforgettable. Betelgeuse, with its immense mass, has no alternative destiny. Its life is a ticking clock, and when that clock runs out, the collapse of its core will set off a chain reaction so violent that it will tear the star apart in a matter of seconds. To understand why Betelgeuse is headed toward a supernova, we must return to its core. As explained before, Betelgeuse is rapidly burning through heavier and heavier elements, creating an onion-like structure with shells of fusion stacked on top of one another. At the very center, silicon fusion will eventually produce iron. And that's where the story reaches its critical turning point. Unlike lighter elements, iron cannot be fused into heavier elements in a way that releases energy. Instead, trying to fuse iron consumes energy. This means that once iron builds up in the core, fusion grinds to a halt. At this moment, Betelgeuse will lose the delicate tug-of-war that has defined its entire life. Throughout its existence, the outward pressure from fusion has pushed against the inward pull of gravity, keeping the star balanced. But without fusion to supply that pressure, gravity wins. The iron core will collapse in less than a second, shrinking from a size of thousands of kilometers across to just tens of kilometers. This sudden collapse will cause the outer layers of the star to plummet inward, only to rebound in a titanic shockwave. That shockwave, powered by the release of unimaginable amounts of energy, will rip through the star and blow it apart in a brilliant explosion. This is Betelgeuse's fate, a Type II supernova, a cataclysm so powerful that it will briefly rival the brightness of the moon in our sky. When it happens, Betelgeuse's light will transform our night sky and become one of the most spectacular astronomical events in human history. For astronomers, Betelgeuse's eventual supernova is more than just a light show. It is a once-in-a-lifetime opportunity to study a massive star's death up close. Because Betelgeuse is only about 640 light-years away, practically in our galactic backyard, the explosion will provide an extraordinary amount of data. Most supernovae studied in detail are thousands or millions of light-years away, but Betelgeuse's proximity makes it a cosmic gift to science. We will be able to observe every stage of the explosion in unprecedented detail, from the flood of neutrinos to the blast of radiation to the expanding shockwave that will eventually create a glowing nebula. Culturally, Betelgeuse's supernova will be just as transformative. Imagine stepping outside on a clear night and seeing a new star in the sky, one so bright it casts shadows on the ground. Imagine children born under a sky forever marked by the presence of that glowing remnant, a reminder that we are living in an era of cosmic drama. Ancient peoples once recorded supernovae as omens, painting them into the annals of history. When Betelgeuse goes, we will add our own chapter to that story. But this time, with the knowledge that we are watching the natural life cycle of a massive star unfold before our eyes. It's important to emphasize that Betelgeuse's fate as a supernova is not a possibility. It is a certainty. The only unknown is when. It could be tomorrow. It could be 100,000 years from now. But in cosmic terms, that is still soon. Betelgeuse has entered the final, unstable stages of its life. And when its time comes, its death will not be quiet. It will be an explosion that shakes the heavens and reminds us of both the destructive power and the creative potential of the stars. When we talk about Betelgeuse's inevitable end, it's easy to picture it simply as a star blowing up. But the mechanics of a supernova are far more intricate, violent, and awe-inspiring than that simple image suggests. To truly grasp what's coming for Betelgeuse, we need to dive into the supernova process itself, a chain of events triggered in less than the blink of an eye, yet releasing more energy in that moment than our Sun will emit across its entire 10 billion-year lifetime. It all begins with the iron core. As Betelgeuse nears its final stages, successive layers of fusion will have stacked up inside it. Hydrogen burning on the outside, then helium, carbon, neon, oxygen, and silicon, all fusing closer and closer to the center. Each of these processes produces heavier elements until silicon finally creates iron. But iron is the dead end of nuclear fusion. Unlike lighter elements, which release energy when fused, iron requires energy to fuse. This means no new outward pressure can be generated in the core. Once enough iron accumulates, the core becomes unstable. Gravity, which has been trying to crush the star inward all along, suddenly gains the upper hand. The core collapses catastrophically in fractions of a second, shrinking from a sphere thousands of kilometers across to something only about 30 kilometers wide, a neutron star core. To put that in perspective, the entire mass of our Sun compressed into an object smaller than Manhattan. The density at this stage is unimaginable. A teaspoon of neutron star material would weigh billions of tons. The collapse accelerates so quickly that even atoms themselves are destroyed. Electrons are crushed into protons, creating neutrons and releasing a flood of neutrinos, ghost-like particles that rarely interact with matter. This neutrino burst carries away an enormous fraction of the collapsing star's energy. Yet because neutrinos interact so weakly, most of them escape into space almost instantly. In fact, neutrinos are the very first signal scientists expect to detect when Betelgeuse finally goes supernova, arriving hours before the light of the explosion reaches Earth. As the core slams to a halt at neutron star density, the infalling outer layers of the star rebound violently. A shockwave races outward through the collapsing star. At first, this shockwave stalls, threatened by the immense gravitational pull and the density of the surrounding layers. But then something extraordinary happens. Neutrinos flooding out of the core deposit energy into the material just above it, re-energizing the shockwave. With this boost, the shockwave reignites and surges outward with unstoppable force, tearing through the star's layers. In this moment, Betelgeuse becomes a Type II supernova, an explosion so powerful that it outshines the combined light of hundreds of billions of stars in its galaxy. The energy released is almost incomprehensible, on the order of 10 joules. To compare, that's about the total amount of energy our Sun will radiate over its entire existence, unleashed by Betelgeuse in just a few seconds. The outer layers of Betelgeuse, once suspended gracefully around its bloated red supergiant body, are blown into space at speeds of thousands of kilometers per second. The star that once loomed so large will be obliterated, leaving behind only a compact core, either a neutron star or, if Betelgeuse's mass is high enough, perhaps even a black hole. But the violence of this process is not just destructive, it is profoundly creative. The shockwave heats and compresses matter to such extremes that new heavy elements, gold, uranium, and other building blocks of planets and life, are forged in the explosion. These elements are hurled into the surrounding interstellar medium, enriching the galaxy. Betelgeuse's death, violent as it will be, ensures that future generations of stars and planets will carry the seeds of new worlds. From the perspective of Earth, this entire process, the collapse, rebound, neutrino flood, and explosion, will play out invisibly until the light of the blast arrives. When it does, Betelgeuse will appear to flare in our skies with astonishing brilliance, a beacon of both destruction and rebirth. So while the phrase Betelgeuse will explode may sound simple, the truth is anything but. The death of a massive star is one of the most extreme physical processes the universe allows, a collision of gravity, quantum physics, and nuclear forces that culminates in the brightest light show the cosmos has to offer. And Betelgeuse is the next candidate on that cosmic stage. When Betelgeuse finally explodes, it won't be a subtle event buried in the night sky, detectable only by advanced telescopes. No, it will be a cosmic spectacle so dramatic that even those who have never once looked up with curiosity will notice it. The brightness of Betelgeuse's supernova will be unlike anything humanity has ever witnessed in recorded history. For thousands of years, Betelgeuse has been a red jewel on Orion's shoulder, a star among stars. But in the moment of its death, it will transform into something that rivals the very brightest objects in our sky. Astronomers predict that the explosion could reach a magnitude of -12 or even brighter, making it at least as luminous as the full moon, and possibly outshining it. Unlike most celestial phenomena, which are confined to the darkness of night, Betelgeuse's supernova will be visible in broad daylight for weeks or even months. Imagine stepping outside under a clear afternoon sky and seeing a blazing point of light rivaling Venus, Jupiter, or even the moon, but knowing that it is a star dying 640 light-years away. This isn't speculation plucked from thin air. Humanity has seen echoes of such events in the past, though never so close. The Chinese astronomers of the Song dynasty famously recorded the supernova of 1054, which created what we now call the Crab Nebula. That star was located about 6,500 light-years away, 10 times farther than Betelgeuse, yet it was visible in the daytime sky for nearly a month. Betelgeuse, being much closer and much more massive, will be even more spectacular. The brightness will unfold in stages. When the explosion begins, Betelgeuse will suddenly brighten by orders of magnitude. Within hours or days, it will outshine every star and planet in the sky. At its peak, its light will be so intense that it will cast shadows on the ground at night, as though we had two moons in the sky. Stargazing will never be the same during that period. Orion's familiar outline will be shattered, dominated by this blinding beacon. The supernova will remain dazzling for weeks, possibly months, before gradually fading. Even after the initial flare subsides, the fading ember of Betelgeuse will still be brighter than most stars, remaining a fixture in our skies for years. Over time, the explosion will leave behind a glowing remnant nebula, a cloud of gas and dust illuminated by the energy of the blast. Future generations may look up at Orion and see not Betelgeuse, but a spectacular glowing nebula where it once resided, a permanent reminder of the star's death and rebirth. What makes this event so astonishing is that it will be witnessed across the entire planet. Unlike solar or lunar eclipses, which are localized to specific regions, Betelgeuse's explosion will be a global event. No matter where you are on Earth, whether in the crowded streets of a city or the remote expanse of a desert, the supernova will be visible. It will unite humanity in awe, just as comets, eclipses, and past supernovae have done throughout history. For science communicators, artists, and storytellers, the brightness of Betelgeuse's supernova will ignite inspiration. For astronomers, it will provide a once-in-a-lifetime opportunity to study the physics of supernovae up close, using every tool available, from neutrino detectors to space-based observatories. For ordinary people, it will be a chance to experience the living, dynamic nature of the universe, to feel connected to something vast and timeless. And yet, even in its brilliance, Betelgeuse's supernova will serve as a humbling reminder of scale. We are talking about a star so far away that its light has been traveling for 640 years just to reach us. The explosion itself may have already happened, centuries ago, and we are merely waiting for its light to arrive. When it does, it will fill our skies with brilliance, proof that even across cosmic distances, the life and death of stars can touch us directly. So when Betelgeuse finally unleashes its fury, it will not only reshape Orion in our night sky, it will etch itself into the memory of every human being alive to see it. For a brief period in cosmic history, we will all live under the glow of a dying star, brighter than the moon, visible in the day, and unforgettable in its magnificence. Long before Betelgeuse's explosion dazzles our skies with blinding light, an invisible messenger will whisper its fate to us. That messenger is the neutrino, a ghost-like particle that passes effortlessly through matter, rarely interacting with anything at all. Neutrinos are born in immense numbers during the final collapse of a massive star, and they travel across the cosmos almost completely, unimpeded. In fact, when Betelgeuse finally goes supernova, we won't see it first, we'll detect it through neutrinos. Here's how it works. During the core collapse, as the iron core of Betelgeuse implodes, electrons are forced to combine with protons, creating neutrons and releasing a vast burst of neutrinos. This burst happens in an instant. In less than a second, the star produces more neutrinos than it has in its entire lifetime up to that point. These neutrinos carry away an astonishing amount of energy, about 99% of the total released in the explosion. To give a sense of scale, that's more energy than all the stars in the universe emit in visible light at any given time, streaming outward from one dying star in a near-invisible flood. Because neutrinos are almost massless and interact so weakly with matter, they escape the collapsing star long before photons of light do. Light from the explosion must battle its way out of the star's dense layers of gas, a process that takes hours. Neutrinos, on the other hand, slip through virtually unimpeded and begin racing toward Earth at nearly the speed of light. This means that when Betelgeuse goes supernova, the first alert we'll get won't be visual. It will be a sudden, global surge in neutrino detectors here on Earth. We already have a network of observatories capable of catching these elusive particles. Facilities like Kamiokande in Japan, IceCube in Antarctica, and other underground neutrino detectors are constantly watching for sudden bursts. When the day comes, those instruments will light up with an unmistakable signal, millions of neutrinos arriving almost simultaneously. Scientists call this an early warning system, because it will tell us the explosion has happened hours before the light itself reaches us. This is not just theory. In 1987, when a supernova erupted in the Large Magellanic Cloud, about 168,000 light-years away, neutrino detectors on Earth registered a handful of events mere hours before the supernova's light became visible. That event, known as SN 1987A, was the first direct confirmation that neutrinos are the heralds of stellar death. When Betelgeuse explodes, the neutrino burst will be thousands of times stronger, giving us an unmistakable signal. Imagine the drama of that moment. Somewhere in a laboratory deep underground, computers monitoring neutrino detectors will suddenly spike with activity. Within seconds, alerts will go out across the world to observatories, scientists, and space agencies. Betelgeuse has gone supernova. Hours later, people will look up and see the sky transformed by the brightest stellar explosion in human history. But by then, astronomers will already know it's coming. Humanity will essentially get a short cosmic countdown to the light show. For astronomers, this neutrino burst will be more than just a warning. It will also be a priceless treasure trove of data. Neutrinos are the only direct messengers from deep inside the core of a collapsing star, carrying with them information about the physics of the collapse itself, conditions of density, pressure, and energy that no laboratory on Earth can replicate. By studying Betelgeuse's neutrino burst, scientists will unlock secrets of how massive stars die, how shockwaves are triggered, and even how exotic states of matter behave at nuclear densities. The beauty of this is that while neutrinos are invisible to us, we cannot see them, feel them, or stop them. They will be our first connection to Betelgeuse's final moment. They will arrive silently, unnoticed by human senses, but ringing loudly in the ears of our detectors. In that quiet instant, before the star's light even touches our eyes, we will already know that one of the greatest events in human astronomical history has begun. So when Betelgeuse finally explodes, remember this: the skies won't surprise us. The neutrinos will. They are the first whisper of a cosmic scream, the opening act in a finale that will light up our world. When Betelgeuse finally detonates, Earth's night sky will never look the same. Not for weeks, not for months, and perhaps not even for years. The familiar constellations we have traced for thousands of years will be temporarily rewritten by the sheer brilliance of a single star's death. For stargazers, casual observers, and even those who rarely glance upward, Betelgeuse's supernova will dominate the heavens in a way that no one alive has ever experienced. At the very peak of the explosion, Betelgeuse will blaze with a light comparable to the full moon. But unlike the moon, which presents a wide glowing disk, Betelgeuse will appear as a dazzling pinpoint, sharp, intense, and almost otherworldly. Imagine looking up into Orion, expecting the familiar red shoulder, and instead seeing a blazing beacon so bright it casts shadows at night. The stars we once used to outline Orion's body will pale next to it. Even Rigel, Orion's other jewel, will fade into insignificance. For that period, Betelgeuse will not just be a star in Orion, it will be Orion. This transformation won't be fleeting. Astronomers estimate that Betelgeuse's supernova could remain brighter than Venus for several months, easily visible even in the daytime sky. Night after night, generations of humans will look up and see a new celestial companion, brighter than anything else, glowing with the fury of a dying star. For those months, stargazing will take on a completely new character. Astronomy apps, planetarium software, and star charts will all look oddly incomplete, because they were never designed to account for such brilliance in Orion. The effect will ripple far beyond the scientific community. Imagine how cultural traditions tied to Orion might shift, how poets, storytellers, and artists will interpret this brilliant star's farewell. Just as comets, eclipses, and supernovae have influenced mythology and art throughout history, Betelgeuse's explosion will inspire a new wave of creativity. For children born in that era, the idea of Orion without a blazing light at its shoulder will seem strange, until the supernova fades, and they realize that stars, too, have lifespans. And fade it will, but slowly. After the initial months of brilliance, Betelgeuse will gradually diminish in brightness, though it will still be visible long after it has stopped dominating the sky. Over the years, what remains will no longer be a star but a nebula, glowing with the energy of the explosion. Orion, which has been one of the most recognized constellations in human history, will wear a new adornment, a colorful, expanding cloud of gas and dust, much like the Crab Nebula left behind by the supernova of 1054. Future stargazers might point to Orion not for its hunter's outline, but for the nebula where a once mighty star breathed its last. For astronomers, this will be a golden age of observation. Telescopes across the globe and in space will train on Betelgeuse's remnant, studying how the explosion evolves over time. The night sky won't just change for the public, it will transform into a living laboratory, one of the most important natural experiments in modern science. Every night for years, researchers will be piecing together the physics of stellar death, guided by the fading glow of Betelgeuse. But beyond science, there's something deeply human about what the night sky will become. For millennia, humanity has looked to Orion as a cultural touchstone. The Egyptians aligned pyramids with its stars. Greek mythology imagined the figure of a hunter striding across the heavens. Indigenous cultures across the world have their own stories tied to its pattern. Betelgeuse's supernova will unify those traditions in a single moment of awe, reminding us that we are all bound under the same sky. It's also worth noting how personal the sky feels to many. Amateur astronomers who've spent decades tracing constellations will suddenly find their charts incomplete. Sky photographers will capture images unlike anything ever seen. Parents will point to the glowing beacon and tell their children, "That's Betelgeuse, a star dying so far away its light has taken centuries to reach us." For those children, the night sky will never again be an abstract map of faraway points. It will be alive, changing, and immediate. In short, Betelgeuse's explosion will not just brighten the night, it will reshape humanity's relationship with the cosmos. For a generation of stargazers, Orion will be remembered not as it always was, but as it appeared during that extraordinary moment when one of the universe's giants gave its final, unforgettable farewell. Whenever people hear that a star as enormous as Betelgeuse is on the verge of exploding, the first instinctive question is often, will this hurt us? It's a reasonable concern. After all, the idea of a star unleashing more energy in seconds than our sun will release over billions of years sounds terrifying. But here's the truth, while Betelgeuse's supernova will be a spectacular event, Earth is far enough away to be completely safe from any direct harm. Betelgeuse sits roughly 640 light-years from us. To a human scale, that distance is incomprehensible, but in astronomy, it's practically next door. Still, it is not nearly close enough for the explosion to pose a danger. Scientists generally estimate that a supernova would need to occur within about 25 to 30 light-years of Earth to have a significant negative impact on our planet's biosphere. That's the distance at which high-energy radiation, particularly gamma rays, could potentially strip away parts of our ozone layer, increase harmful solar and cosmic radiation at Earth's surface, and cause long-term damage to life. Betelgeuse, being more than 20 times farther away than this danger zone, poses no such threat. When it explodes, the most dangerous forms of energy, intense bursts of gamma rays, high-energy cosmic rays, and other deadly radiation, will have dissipated across the vast gulf of interstellar space by the time they reach us. What we will experience instead is the safe and awe-inspiring spectacle of light, neutrinos, and eventually, the glowing debris cloud of a new nebula. To put it into perspective, think of it like watching a massive fireworks display from hundreds of miles away. You see the light, maybe you feel the faintest rumble if you are close enough, but you are in no danger from the explosion itself. In fact, the radiation reaching us from Betelgeuse's death will be so harmless that you could look at it with the naked eye, something you would never dare to do with our own sun. This distinction is important, because throughout history, supernovae have been met with fear as well as awe. Ancient civilizations often interpreted them as omens of disaster, sudden bright stars appearing in the heavens with no explanation. Today, we know better. We understand the physics, the distances, and the thresholds of danger. Betelgeuse's supernova, when it comes, will be awe-inspiring, not apocalyptic. Even astronomers, who are among the most cautious when predicting cosmic threats, are in agreement. Betelgeuse's explosion will not harm Earth. The only danger is perhaps to our sense of cosmic scale, reminding us just how small we are compared to the titanic forces at work in the universe. If anything, we should feel lucky. Lucky that such an event is happening close enough to witness, but not so close as to threaten us. We're in the perfect cosmic vantage point, near enough to watch in wonder, far enough to remain untouched. Future generations may remember this as one of humanity's greatest strokes of astronomical luck, to be alive at the time when a red supergiant so near to us chose to end its life in the most spectacular way imaginable. So to reassure everyone, when Betelgeuse does go supernova, you won't need to worry about radiation storms frying satellites, you won't need to fear the collapse of ecosystems, and you won't need to imagine the end of the world. The only thing you'll need to do is step outside, look up, and witness one of the most magnificent shows the universe has to offer. When we talk about a star exploding in a supernova, one of the most intimidating aspects is the radiation it unleashes. A supernova isn't just a pretty light show. It's a cosmic blast furnace releasing staggering amounts of high-energy particles and waves. Among these are gamma rays and cosmic rays, forms of radiation so powerful that, under the wrong circumstances, they could devastate life on a nearby planet. And this is why many people worry, if Betelgeuse explodes, will all that radiation wash over Earth? The reassuring answer is no. Let's break this down. A supernova like Betelgeuse's will produce an enormous burst of gamma rays, the highest energy photons in the electromagnetic spectrum. Unlike visible light, which we see with our eyes, or radio waves, which carry our phone signals, gamma rays are extremely energetic and destructive. If Betelgeuse were only, say, 20 light-years away, that gamma-ray burst could potentially deplete parts of Earth's ozone layer, exposing us to harmful ultraviolet light from the sun and sparking cascading ecological effects. Some scientists even hypothesize that past mass extinctions on Earth might have been influenced by nearby supernovae in our galaxy. But here's the key: gamma rays spread out as they travel. Imagine lighting a candle. If you're standing a meter away, the flame feels hot. If you're standing 100 meters away, the heat becomes negligible. Betelgeuse, at around 640 light-years, is vastly outside the danger zone. By the time its gamma rays reach us, they will have spread so thinly across the cosmos that they'll be nothing more than harmless background energy. Then there are cosmic rays. These are high-speed atomic nuclei and subatomic particles flung into space by the explosion. They zip through the galaxy at nearly the speed of light, colliding with atoms and creating showers of secondary particles when they strike matter. In large doses, cosmic rays can damage DNA, disrupt satellites, and pose hazards to astronauts. Once again, though, distance is our friend. At 640 light-years away, Betelgeuse's cosmic ray contribution will be insignificant compared to the cosmic rays we already deal with every day, many of which come from far more distant supernovae or active galaxies. In fact, every second, trillions of cosmic rays pass through your body without you even noticing. The contribution from Betelgeuse, when the time comes, will be indistinguishable against this cosmic background noise. Some people also ask about focused radiation, particularly gamma-ray bursts, GRBs. These are extremely concentrated beams of energy released by certain kinds of stellar deaths, like collapsing massive stars spinning at incredible speeds. If a GRB were ever aimed directly at Earth from a nearby system, it could be catastrophic. But here's the catch: Betelgeuse is not the right kind of star to produce such a jet. GRBs typically come from rapidly rotating, stripped-core stars known as Wolf-Rayet stars, not bloated red supergiants like Betelgeuse. So we can strike that worry off the list entirely. What remains for us, then, is the light show without the danger. We will get the neutrino flood, we will see the brilliant glow brighter than the moon, and we will eventually observe the expanding nebula where Betelgeuse once lived. What we will not get is a wave of harmful radiation capable of threatening life on Earth. And in a way, this adds to the poetry of it. Betelgeuse will unleash unimaginable power, but across the gulf of space, that power will be transformed into nothing more than awe. The dangerous radiation will be diluted into invisibility, while the beauty of the light will shine forth for all of humanity to see. It's as though the universe itself has gifted us the perfect distance, close enough to inspire wonder, far enough to keep us safe. So when Betelgeuse explodes, remember this: it will not scorch our world, it will not poison our atmosphere, and it will not be a cosmic threat. It will simply light up our skies with a brilliance that makes us pause, reflect, and marvel at the universe we live in. To truly appreciate why Betelgeuse is safe, it helps to compare it to hypothetical closer threats. A supernova is not just a spectacle, it is also a release of staggering amounts of energy, and proximity matters. If Betelgeuse were within 30 light-years of Earth, our story would be dramatically different. At that distance, the gamma rays, X-rays, and cosmic rays produced by the explosion could interact with our atmosphere in dangerous ways. Gamma rays are the primary concern for life on Earth. A supernova close enough could strip away significant portions of the ozone layer, leaving the planet exposed to harmful ultraviolet radiation from the sun. This could lead to widespread ecological damage, crop failures, and increased rates of cancer and genetic mutations for living organisms. Cosmic rays could further exacerbate this effect, flooding the atmosphere with high-energy particles that could penetrate deeply into the biosphere. In short, a supernova within 30 light-years could be catastrophic. Fortunately, Betelgeuse is far beyond that danger zone, sitting roughly 640 light-years away. That distance is more than 20 times the critical threshold for concern. By the time the explosion's gamma rays and cosmic rays reach Earth, they will have dispersed across such a vast distance that they pose no significant threat. Our planet will be left untouched, receiving nothing more than a spectacular light show and a gentle influx of neutrinos, which, as discussed, are harmless. To put this into perspective, imagine two fireworks displays. One is set off a few feet away from you, so close that the heat singes your skin. The other is launched miles away, so that you see the brilliant flashes of color but feel no heat and are entirely safe. Betelgeuse is that distant firework, magnificent, impossible to ignore, but entirely safe because of the vast cosmic separation between us. Even stars closer than Betelgeuse are generally not dangerous. For a supernova to threaten Earth, it would need not only to be within 30 light-years, but also oriented in a way that any gamma-ray burst or focused radiation could directly impact our planet. Luckily, most massive stars in our galaxy, including Betelgeuse, are simply too far away for their deaths to harm us. This is a cosmic stroke of luck, considering how powerful and destructive these explosions can be. Interestingly, the comparison to a closer threat helps underscore just how fortunate we are to live when Betelgeuse is nearing its end. If it were 600 light-years closer, around the threshold of danger, humanity would not be looking forward to a light show. We would be preparing for a survival scenario, where the fate of ecosystems and life itself could be at stake. The universe has placed Betelgeuse at just the right distance, close enough to witness its grandeur, far enough to remain completely safe. This also highlights an important distinction between awe and anxiety. The danger from a supernova is entirely a function of distance. For Betelgeuse, all the fear-inducing properties of a massive explosion exist: gamma rays, cosmic rays, neutrinos, shockwaves, but the vast interstellar gulf between us and the star transforms that raw destructive power into beauty. The universe has provided humanity with a front-row seat, with no risk to life, to witness one of the most extreme events imaginable. After Betelgeuse's dramatic supernova explosion, what remains is not just the fading light in our sky, but the stellar remnant at its core, the dense, compact object left behind after the star's outer layers have been blasted into space. This remnant will be one of the most extreme forms of matter in the universe, either a neutron star or, if conditions allow, a black hole. Understanding this final stage is crucial because it illustrates the incredible extremes of physics and matter, and it also tells us how Betelgeuse continues to shape the cosmos even after its death. Let's begin with the more likely outcome, a neutron star. When the iron core collapses during the supernova, the matter is crushed to such a density that protons and electrons merge to form neutrons. What results is an object typically only about 20 kilometers in diameter, roughly the size of a small city, but containing more mass than the Sun. To put that in perspective, a single teaspoon of neutron star material would weigh billions of tons. This incredible density means that neutron stars are held together by gravity so strong that ordinary atomic structures cannot exist. The neutrons are packed so tightly that they form essentially a giant atomic nucleus. Neutron stars can spin extremely rapidly, sometimes hundreds of times per second, and they often generate intense magnetic fields trillions of times stronger than Earth's. Some neutron stars emit beams of electromagnetic radiation from their magnetic poles, producing the phenomena we call pulsars. If Betelgeuse's remnant becomes a pulsar, it would act like a cosmic lighthouse, sending precise, rapid flashes of radiation across space for thousands to millions of years. Scientists on Earth could detect these pulses and study the remnant in remarkable detail, long after the supernova itself fades from view. However, there is another possibility. If Betelgeuse's core is slightly more massive than expected, the gravitational collapse may not stop at a neutron star. Instead, it could continue collapsing into a black hole, an object with gravity so intense that not even light can escape from it. In that case, Betelgeuse would leave behind a singularity, a point of infinite density, surrounded by an event horizon, the boundary beyond which nothing can return. Black holes formed from supernovae are smaller than stellar mass black holes like those observed in X-ray binaries, but their formation is no less dramatic. The star's death would not only have created a brilliant explosion but also a gravitational well so deep that it distorts space and time around it. Whether Betelgeuse leaves behind a neutron star or a black hole, its remnant is a lasting testament to the power of stellar evolution. The explosion distributes heavy elements into space, enriching the interstellar medium, while the remnant becomes an object of immense scientific interest. Neutron stars and black holes serve as natural laboratories for physics under conditions we cannot reproduce on Earth, allowing us to study matter at nuclear densities, extreme magnetic fields, and the limits of Einstein's theory of general relativity. This remnant also has implications for the future of our galaxy. The energy and mass expelled during the supernova will interact with surrounding gas clouds, triggering the collapse of nearby regions and the formation of new stars and planets. Over millions of years, Betelgeuse's death will contribute to the cosmic recycling that builds galaxies and, eventually, life. Meanwhile, its core, whether as a pulsar or a black hole, will persist as a silent, mysterious monument to the star that once dominated Orion's shoulder. In essence, the remnant is both an ending and a beginning. The supernova ends the life of Betelgeuse as a luminous red supergiant, but its core, compact, extreme, and invisible to the naked eye, marks the start of a new phase of cosmic influence. The neutron star or black hole left behind will continue to interact with its surroundings, sending ripples across space-time, guiding the paths of nearby matter, and offering a window into some of the most extreme physics in the universe. Betelgeuse's death is not just an ending, it is the beginning of a new cycle in the universe. The supernova explosion will scatter the elements forged deep within the star into space, seeding the interstellar medium with the building blocks for future generations of stars, planets, and even life itself. This process, often referred to as cosmic recycling, is one of the most profound ways in which massive stars influence the evolution of the cosmos. To understand this, we need to consider what happens inside a star like Betelgeuse during its life. As it ages, the star undergoes successive stages of nuclear fusion, creating progressively heavier elements in its core. Hydrogen fuses into helium, helium into carbon and oxygen, carbon into neon, neon into oxygen, oxygen into silicon, and finally silicon into iron. These reactions take place under extreme temperatures and pressures, producing elements that cannot be formed under normal conditions. Essentially, Betelgeuse acts as a cosmic factory, creating the very materials that will one day make planets, asteroids, and even living organisms possible. But these elements are trapped inside the star until its violent death. When Betelgeuse explodes as a supernova, the energy released in the blast ejects its outer layers into space at thousands of kilometers per second. Hydrogen, helium, and the newly forged heavier elements such as carbon, oxygen, magnesium, silicon, and iron are hurled into the surrounding interstellar medium. These materials mix with existing gas and dust, enriching the galaxy with the ingredients necessary for new star systems. Without massive stars like Betelgeuse, the universe would remain a simpler place, dominated by hydrogen and helium, lacking the rich diversity of elements needed for planets and life. This cosmic recycling also demonstrates the continuity of matter in the universe. The oxygen we breathe, the calcium in our bones, the iron in our blood, and the golden jewelry were all once forged in the cores of massive stars and dispersed into space by supernovae. In a very real sense, every human being is a product of stellar alchemy, composed of materials that were once part of long-dead stars. Betelgeuse's explosion will contribute to this ongoing process, ensuring that future stars and planets inherit the heavy elements necessary to form complex worlds. The influence of Betelgeuse's supernova will extend far beyond its immediate neighborhood. The shockwave from the explosion will sweep up surrounding clouds of gas and dust, compressing them and potentially triggering the birth of new stars. In some regions, the shockwave may even trigger the formation of entire stellar clusters. Over millions of years, these elements will become part of new planetary systems, some of which could eventually harbor life. The star that once shone as the red shoulder of Orion will, in a sense, become part of new suns, new planets, and perhaps new living beings. Cosmic recycling is a powerful reminder that death in the universe is rarely final. Betelgeuse's life ended in fire and explosion, but that same death is the seed of creation. The elements it produces are fundamental to the ongoing evolution of galaxies. They are the raw material for planets like Earth, for atmospheres, for oceans, and for all the complexity that arises in the universe. The supernova is both an end and a beginning, a transformation that ensures the universe continues to evolve in richness and diversity. Furthermore, the heavy elements distributed by Betelgeuse's supernova will leave chemical fingerprints in future stars and planetary systems. Astronomers can study these fingerprints in distant stars to understand the history of supernovae in the Milky Way. In this way, Betelgeuse will continue to educate scientists long after its death, as the elements it forged are incorporated into new generations of stars. The cycle of death and rebirth is written in the very atoms of the cosmos, with Betelgeuse poised to make its next contribution. In short, Betelgeuse's supernova is not only a spectacular visual event but also a crucial step in the ongoing evolution of the universe. Through cosmic recycling, it will sow the seeds of new stars and planets, continue the cycle of matter, and ensure that even in death, Betelgeuse contributes to the beauty, complexity, and life-bearing potential of the cosmos. It's a vivid reminder that the universe is an interconnected system, where endings are inseparable from beginnings, and where the grandeur of a single star can ripple through time and space, shaping the destiny of countless future worlds. Throughout history, humanity has occasionally been gifted glimpses of stellar cataclysms, bright supernovae that suddenly appeared in the night sky, transforming familiar constellations and capturing the imagination of those who witnessed them. Comparing Betelgeuse's impending explosion to these historical events helps put its significance into context and highlights just how extraordinary it will be when it finally occurs. One of the most famous historical supernovae is SN 1054, recorded by Chinese, Japanese, and Arab astronomers. This star erupted in the constellation Taurus over 950 years ago, creating a brilliant new light in the sky. Ancient observers described it as a guest star that shone brightly during the day for weeks, an event so remarkable that it was meticulously recorded in historical chronicles. SN 1054 eventually faded from naked eye visibility, but the material it expelled formed what we now call the Crab Nebula, a glowing cloud of gas and dust still studied extensively by astronomers today. Other notable supernovae include SN 1572, observed by the Danish astronomer Tycho Brahe, and SN 1604, recorded by Johannes Kepler. These events, like SN 1054, were visible to the naked eye and startled humanity with their sudden appearance. However, all of them occurred at distances much farther than Betelgeuse, several thousand light-years away. While they were remarkable in their own right, their light could only briefly rival the Moon, and none were as close as Betelgeuse will be. Betelgeuse is unique in that it is relatively close in cosmic terms, only about 640 light-years away. This means that when it goes supernova, the brightness we see will be unprecedented in human experience. Whereas SN 1054 required careful observation to fully appreciate, Betelgeuse's explosion will dominate the night sky, likely visible even during daylight hours. It's as if history's brightest guest stars are being upgraded into a supernova performance on a planetary scale, visible across continents, impossible to ignore, and unforgettable for anyone alive at the time. The comparison also shows the continuity of stellar evolution in the galaxy. Supernovae like SN 1054 and SN 1604 are not isolated phenomena. They are part of an ongoing cycle of birth, life, death, and rebirth that shapes the Milky Way. Betelgeuse's supernova will be another chapter in this cosmic story, providing both a spectacle and a scientific laboratory for humanity, just as SN 1054 gifted the Crab Nebula to astronomers. The Crab Nebula itself continues to evolve, providing insight into the physics of supernova remnants and neutron stars, which hints at what we might observe with Betelgeuse's aftermath. Historically, supernovae also remind us of the fleeting nature of cosmic events. The stars we see in the sky appear eternal, but Betelgeuse teaches us that even giants have lifespans. While the historical supernovae faded within months or years, their remnants persist for millennia, continuing to shape the galaxy. Betelgeuse will follow the same pattern, a sudden, dazzling appearance, followed by a long-lived nebula and, perhaps, a compact remnant like a neutron star or black hole. Comparing Betelgeuse to these past events emphasizes just how fortunate we are to live in this epoch. Ancient civilizations observed guest stars and often interpreted them as omens, without understanding the physics behind them. We, however, have the knowledge, telescopes, and detectors to study every stage of the explosion, from the early neutrino burst to the expanding nebula. It will be the first supernova in recorded human history close enough to be studied in such extraordinary detail while still being safe to observe. In short, Betelgeuse will not just echo the historical supernovae that left their marks in the sky and in our chronicles. It will surpass them in scale and proximity, offering both a stunning visual experience and an unprecedented scientific opportunity. It is, in a sense, history repeating itself. Only this time, humanity will be fully prepared to witness, study, and understand it. Despite all we know about Betelgeuse's size, composition, and instability, there remains a humbling truth. We cannot predict exactly when it will explode. The universe, as vast and well-studied as it may seem, retains an element of unpredictability, especially when it comes to the final moments of a star's life. For Betelgeuse, this uncertainty spans a scale from the almost immediate to the extraordinarily distant. It could go supernova tomorrow, or it could take another 100,000 years before its life ends in spectacular fashion. The unpredictability arises from the complex processes occurring in Betelgeuse's core. As a red supergiant, it has already exhausted hydrogen and helium in its center and is burning heavier elements in successive shells around the core. Eventually, silicon fusion will create iron, a dead-end element for fusion. At that point, the core will collapse under gravity, initiating the supernova. While we can model these processes with remarkable precision in theory, the exact timing depends on microscopic variations in temperature, density, and fusion rates within the core, factors that are extremely difficult to observe or calculate from 640 light-years away. Even small differences in these conditions can translate into huge variations in when the explosion occurs. In cosmic terms, soon can still mean tens of thousands of years, or far off could still be only a few decades. Betelgeuse's great instability, its swelling, pulsations, and variable brightness, gives clues that it is nearing the end of its life, but these signs cannot pinpoint a precise day, year, or century. Its behavior could remain erratic for centuries before finally triggering a core collapse. Astronomers sometimes monitor sudden dimming events, like the famous Great Dimming of 2019 to 2020, for clues that Betelgeuse might be on the verge of exploding. While such events generate excitement and speculation, they do not serve as a countdown. The Great Dimming, caused by dust clouds or temporary surface changes, was initially misinterpreted by some as a signal of imminent supernova. In reality, the explosion could still be centuries or millennia away. This unpredictability adds a layer of suspense and wonder. Every night we look at Orion, we are witnessing a star on the precipice of history, yet we cannot know exactly when it will tip over. This uncertainty also underscores the patience required in astronomy. Human lifetimes are infinitesimal compared to the life cycles of stars, even massive ones like Betelgeuse. A star with a lifespan of millions of years may appear steady to us for generations, yet its inner turmoil could reach a cataclysmic climax at any moment within that time frame. Scientists can estimate a probability range that Betelgeuse is in its final hundreds of thousands of years, that it has entered the last stage of heavy element fusion, but the exact instant is unknowable until it happens. The unpredictability has practical implications as well. Astronomers maintain continuous monitoring, using telescopes and space observatories to track its brightness, surface activity, and spectral lines. Networks of neutrino detectors stand ready to catch the first whisper of collapse. Still, we must accept that, for all our technology and knowledge, we are observers awaiting a cosmic event that is both imminent in astronomical terms and uncertain in human terms. This tension between knowledge and unpredictability is part of what makes Betelgeuse so captivating. Unlike predictable eclipses or planetary transits, a supernova is a natural surprise, a celestial event that could arrive at any moment without warning. It reminds us of our place in the universe, aware of the forces at work, able to anticipate patterns, yet ultimately humble before the immense scale and complexity of stellar life and death. In summary, Betelgeuse's unpredictability, the fact that it could explode tomorrow or tens of thousands of years from now, adds both suspense and wonder to its story. It is a ticking cosmic clock, one that we watch from afar, with the understanding that its final act may unfold within our lifetimes, or long after humanity has changed in ways we cannot imagine. The mystery is part of the beauty, making every glance at Orion a reminder of the delicate balance between knowledge and uncertainty in the universe. Because Betelgeuse could explode at any time, tomorrow, in a century, or tens of thousands of years from now, astronomers maintain continuous monitoring of this extraordinary star. Monitoring Betelgeuse is both a scientific necessity and an opportunity to witness stellar evolution in real time. Thanks to advances in technology, we now have an array of telescopes, space-based observatories, and specialized instruments dedicated to tracking its every flicker, pulse, and fluctuation. One of the most critical aspects of monitoring is observing changes in brightness. Betelgeuse is a variable star, and its luminosity fluctuates over months and years. These variations can provide vital clues about the internal processes of the star. Ground-based optical telescopes, ranging from small amateur instruments to large professional observatories, are constantly measuring its light output. Networks of astronomers around the world contribute data daily, creating a nearly continuous record of how Betelgeuse behaves. This is particularly important because sudden dimming events, like the Great Dimming of 2019 to 2020, can hint at surface activity, mass ejections, or dust clouds forming around the star. By tracking these changes, scientists hope to identify patterns that could precede a supernova. Beyond optical observation, astronomers use infrared telescopes to see through the dust and gas that sometimes obscure the star. Infrared light can penetrate dust clouds, allowing researchers to study both the star's surface and the material it sheds. Instruments like the Very Large Telescope, VLT, in Chile and the Keck Observatory in Hawaii have provided high-resolution imaging of Betelgeuse's surface, revealing enormous convective cells and temperature fluctuations that give insight into the star's instability. Space telescopes like Hubble and Spitzer have also contributed, providing continuous, precise observations unaffected by Earth's atmosphere. Radio telescopes add another layer of information. They detect emissions from the star's outer layers and surrounding material, helping scientists understand how Betelgeuse is losing mass. This is critical because massive stars like Betelgeuse shed huge amounts of material in their final stages. Understanding this mass loss helps refine models predicting when the core might collapse. Facilities such as the Atacama Large Millimeter Submillimeter Array, ALMA, provide unparalleled sensitivity to these emissions, revealing how gases are moving away from the star and forming structures that might influence the timing and nature of the eventual supernova. Neutrino detectors also play a key role. Underground facilities like Kande in Japan, IceCube in Antarctica, and other neutrino observatories are on constant alert for the flood of neutrinos that precedes visible light in a supernova. These detectors are so sensitive that even a tiny uptick in neutrino activity can signal that a catastrophic collapse has begun in the star's core. While neutrinos pass through Earth unimpeded, their detection provides an invaluable early warning system, alerting astronomers hours before the light from the explosion reaches us. Monitoring Betelgeuse isn't limited to professional astronomers. Amateur astronomers worldwide contribute by recording brightness variations and submitting their observations to databases maintained by organizations such as the American Association of Variable Star Observers, AAVSO. This collaborative effort allows for round-the-clock monitoring, ensuring that no significant event goes unnoticed. The combination of multi-wavelength observations, high-resolution imaging, and global collaboration creates an unprecedented surveillance network for Betelgeuse. Every pulsation, surface cooling, or mass ejection is catalogued, analyzed, and compared with theoretical models to improve our understanding of massive star evolution. While we cannot predict the exact moment of explosion, these efforts maximize our preparedness and provide a treasure trove of data for studying the processes that govern supernovae. In essence, Betelgeuse is under a constant scientific spotlight. By integrating data from optical, infrared, radio, and neutrino observatories, humanity has positioned itself to witness, study, and understand one of the universe's most dramatic events in real time. When Betelgeuse finally explodes, we will not be mere passive observers. We will be scientists ready to capture every photon, every particle, and every nuance of a cosmic event that has been millions of years in the making. Betelgeuse has long held a special place in astronomy because it serves as both a living laboratory and a window into the life cycles of massive stars. Studying this red supergiant has taught astronomers more about stellar evolution, the physics of supernovae, and the mechanisms governing the deaths of the universe's most massive stars than almost any other nearby object. Its proximity, size, and variability make it uniquely suited to bridging the gap between theoretical models and observable phenomena. First, Betelgeuse is a textbook example of a red supergiant, a late-stage phase in the life of a massive star. Unlike smaller stars like our Sun, which have relatively stable lifespans measured in billions of years, massive stars burn through their nuclear fuel at a prodigious rate. Betelgeuse's enormous mass, estimated at 15 to 20 times that of the Sun, accelerates its evolution, allowing astronomers to study processes that unfold on human observable timescales, albeit still over decades or centuries. By observing Betelgeuse's pulsations, mass loss, and surface temperature variations, scientists can refine models of how massive stars expand, cool, and prepare for their final explosion. Its variability has also provided a wealth of insight. As a semi-regular variable star, Betelgeuse pulsates in brightness due to convection in its outer layers and instabilities in its extended atmosphere. These fluctuations reveal how energy is transported from the core to the surface and how massive stars lose mass before dying. Observing these cycles over time has helped astronomers understand the role of convective processes in stellar envelopes and how mass ejection events might influence the timing and nature of the eventual supernova. Betelgeuse's impending supernova also makes it a critical case study for supernova physics. The core collapse mechanism, in which iron builds up in the core until it can no longer support itself against gravity, is still not fully understood. By monitoring Betelgeuse in multiple wavelengths and with neutrino detectors, astronomers can capture precursors to core collapse, the neutrino burst that signals the onset of the explosion, and the subsequent light curve of the supernova itself. This allows scientists to test models of energy transport, shockwave propagation, and nucleosynthesis, the creation of heavy elements, in real time. Betelgeuse may provide the first opportunity in history to directly observe a supernova in our galactic neighborhood, giving unprecedented insights into these processes. Another important aspect is Betelgeuse's role in understanding stellar atmospheres and mass loss. Red supergiants like Betelgeuse shed enormous amounts of material through stellar winds, contributing to the enrichment of the interstellar medium with elements necessary for the formation of planets and life. Observations of these processes using infrared, optical, and radio telescopes help astronomers quantify how much mass is lost, how dust forms around massive stars, and how these processes affect the evolution of the star and the surrounding galaxy. Betelgeuse is also a cornerstone for calibrating stellar models. Its brightness, proximity, and size allow astronomers to measure fundamental parameters, such as radius, temperature, and luminosity, with a precision impossible for most distant stars. These measurements help refine theoretical models of stellar structure, providing benchmarks against which other stars can be compared. Essentially, Betelgeuse acts as a Rosetta Stone for understanding the lives and deaths of massive stars. Finally, Betelgeuse has a unique role in public engagement and education. Its visibility in the night sky makes it a natural gateway for people to connect with astronomy. When scientists explain Betelgeuse's instability, potential supernova, and contribution to cosmic recycling, they are teaching the public about nuclear fusion, stellar evolution, and the chemical enrichment of the universe, concepts that are central to understanding our place in the cosmos. In summary, Betelgeuse is far more than a bright point of light in Orion's shoulder. It is a scientific treasure trove, a real-time laboratory for studying massive stars, and a cosmic guide for understanding the life cycles that shape galaxies. By observing its pulsations, monitoring its surface activity, and preparing for its eventual explosion, astronomers gain insights that extend across the fields of stellar physics, nucleosynthesis, and supernova mechanics. Betelgeuse is not just a star, it is a teacher, illuminating the processes that govern the life and death of the most massive stars in our galaxy. To truly grasp the magnitude of Betelgeuse, it helps to compare it directly to our Sun, the star that defines life on Earth. While both stars are powered by nuclear fusion, the scale, energy, and life cycles of Betelgeuse are in a completely different league, a reminder of just how extreme some stars in our galaxy can be. Let's start with mass. The Sun has a mass of approximately 2 × 10³ kilograms, a number almost impossible to comprehend on its own. Betelgeuse, on the other hand, is estimated to be about 15 to 20 times more massive than the Sun. That means if you replaced our Sun with Betelgeuse, you would be adding the equivalent of 15 to 20 suns into a single star, drastically altering the gravitational dynamics of our entire solar system. The sheer mass of Betelgeuse also explains why it lives such a short life. Massive stars burn through their nuclear fuel at a rate exponentially faster than smaller stars. Betelgeuse will exhaust in millions of years, compared to the Sun's lifespan of around 10 billion years. Next, consider size. The Sun's radius is about 700,000 kilometers, but Betelgeuse is a red supergiant nearly 1,000 times larger in radius. If Betelgeuse were placed at the center of our solar system, its surface would extend beyond the orbit of Jupiter, swallowing Mercury, Venus, Earth, Mars, and the asteroid belt without hesitation. This comparison makes it clear that Betelgeuse is not just a bigger sun, it's a colossus among stars, an object whose scale challenges human intuition. When it comes to luminosity, the difference is just as extreme. The Sun emits energy at roughly 3.8 times 10 squared watts, providing the Earth with the warmth and light that sustain life. Betelgeuse, despite being cooler on the surface than the Sun, radiates energy at tens of thousands of times the Sun's total output, because of its enormous surface area. In terms of total energy emitted, it's as though hundreds of thousands of suns were combining their light, producing a star that dominates its local cosmic neighborhood. Even the mass loss rate of Betelgeuse is staggering compared to the Sun. While the Sun loses a tiny fraction of its mass through the solar wind, Betelgeuse sheds thousands of times more material, expelling gas and dust that will eventually seed new stars and planets. Every year, it ejects a volume of material that would dwarf all the mass lost by the Sun over billions of years. This constant shedding of material contributes to its instability and the likelihood of its eventual supernova. The lifespan comparison also emphasizes its extremity. The Sun, relatively small and stable, will continue shining for billions of years. Betelgeuse, massive and hungry, will burn its fuel in mere millions of years. In other words, while the Sun can be thought of as a patient, steady presence in the cosmos, Betelgeuse is a cosmic sprinter, enormous, brilliant, and fated to exhaust itself quickly in a violent, spectacular finale. Finally, there's the supernova potential. While the Sun will quietly expand into a red giant and shed its outer layers gently, Betelgeuse's death will be cataclysmic, releasing more energy in seconds than the Sun will emit over its entire 10 billion-year lifetime. Its supernova will temporarily outshine the Moon and perhaps even the Sun in the daytime sky, an unimaginable scale of energy release when compared to our familiar star. In essence, these comparisons give perspective on just how extreme Betelgeuse is. It is heavier, larger, brighter, and far more short-lived than the Sun, and its final act will be a cosmic spectacle of unimaginable scale. The Sun may be our life-giver, steady and reliable, but Betelgeuse is a stellar titan, reminding us that the universe contains forces and objects that dwarf anything we encounter in our solar system. Observing it teaches us not just about stars, but about the extremes of physics, energy, and the transformative power of massive stars. Whenever Betelgeuse comes up in popular discussions about space, it's often accompanied by dramatic warnings and sensational claims. When Betelgeuse explodes, it will destroy Earth, or we could all be fried by its supernova. While these statements make for thrilling headlines, they are misconceptions that need careful clarification. Understanding the realities behind Betelgeuse's supernova is not only fascinating, but it's also reassuring. The star's explosion, while spectacular, poses no direct threat to life on Earth. First, the distance factor cannot be overstated. Betelgeuse is roughly 640 light-years away, which is incredibly close in galactic terms but astronomically distant in terms of danger. The destructive effects of a supernova, high-energy gamma rays, cosmic rays, and shockwaves, dissipate rapidly as they travel through space. Scientists estimate that for a supernova to pose a real threat to life on Earth, it would need to occur within 25 to 30 light-years. At that proximity, the radiation could damage the ozone layer, increase ultraviolet exposure, and potentially trigger ecological crises. Betelgeuse is far beyond that danger zone, making the notion of Earth's destruction impossible in this case. Second, the type of explosion matters. Betelgeuse is a red supergiant, destined to undergo a core collapse supernova. While this is immensely energetic, it is not the type of event that would produce a focused gamma-ray burst, GRB, aimed at Earth, the phenomenon most often associated with catastrophic planetary effects. GRBs typically come from rapidly spinning, stripped-core stars, not bloated red supergiants. Therefore, the specific mechanism of Betelgeuse's death ensures that its energy will be dispersed broadly across space, rather than focused in a deadly beam. Third, the nature of the danger is often misunderstood. People imagine waves of fire, shock, or radiation that will reach across the galaxy. In reality, by the time Betelgeuse's radiation reaches Earth, the energy will be spread over such a vast area that it will manifest primarily as light, which is entirely harmless. The neutrino burst preceding the visible explosion will pass through our planet unnoticed. Even cosmic rays, while high energy, will be so diluted by the distance that their contribution to Earth's existing cosmic radiation background is negligible. Fourth, many misconceptions arise from misunderstanding timescales. A supernova may appear instantaneous to the human eye, but the physical processes unfold over seconds to minutes, while the light takes centuries to reach us due to the star's distance. The idea that the supernova could arrive suddenly and wreak havoc ignores the realities of cosmic distances and the gradual dispersal of energy over light-years of space. Finally, it's important to separate spectacular visual impact from danger. Betelgeuse's supernova will likely outshine the full moon, be visible in daytime, and dominate the night sky for weeks or months. It will be an unforgettable astronomical event, but the brilliance we see will be a cosmic display rather than a destructive force. Observers can watch safely, and in fact, it will be one of the rare opportunities in history where humanity can witness a nearby supernova without any threat to life or infrastructure. Betelgeuse is a massive, unstable, and potentially dangerous star in theory. The universe has positioned it at a perfectly safe distance. The myths that it could destroy Earth are simply exaggerations, often fueled by the star's dramatic name recognition and the human fascination with cosmic catastrophes. What we can safely anticipate is awe-wond. This clarification is essential because it allows us to enjoy the spectacle without undue anxiety. It emphasizes the point that while the universe contains extreme forces and enormous energies, the laws of physics, distances, and stellar classifications combine to protect us from the most violent events. Betelgeuse will amaze us, inspire curiosity, and illuminate the cosmos, but it will not threaten our planet or species. Exploring what-if scenarios is a fascinating way to understand both the scale of cosmic events and the extraordinary role distance plays in protecting Earth. Betelgeuse's supernova is currently a safe spectacle, but imagining what would happen if it were much closer, say within 30 light-years, highlights the extreme power of these massive stars and why cosmic distance is a crucial shield. If Betelgeuse were only 30 light-years away, the sheer energy output from its supernova would be catastrophic. Gamma rays, normally diluted over hundreds of light-years, would strike Earth with enough intensity to significantly damage the ozone layer, exposing the planet's surface to intense ultraviolet radiation from the sun. This could lead to a cascade of ecological effects: massive die-offs of phytoplankton, disruption of food chains, crop failures, and increased rates of cancer and mutation for terrestrial life. The impact on ecosystems would be profound, and the recovery would likely take decades or centuries. Cosmic rays from such a nearby supernova would also pose a hazard. Unlike light, which travels in a straight line, cosmic rays are high-energy particles that interact with the magnetic field and atmosphere. At only 30 light-years, the flux of these particles could overwhelm Earth's natural shielding, damaging satellites, power grids, and even increasing radiation exposure for humans at high altitudes. Unlike neutrinos, which pass harmlessly through matter, these charged particles can induce atmospheric ionization and contribute to long-term climate and chemical changes. The visual impact would also be extraordinary. Betelgeuse's explosion that close would appear as blindingly bright in the sky, outshining the sun for days, potentially causing temporary blindness if viewed directly. Nighttime skies would be permanently transformed for weeks, with the supernova so intense that stars near it might be obscured by its glare. Unlike its current safe distance, where the light would be awe-inspiring but manageable, a closer explosion could become a hazard to human vision and technology, further demonstrating the critical role of cosmic separation. Even the Earth's atmosphere and biosphere would feel indirect effects. The shockwave from the explosion would take thousands of years to reach us physically, but the increased influx of cosmic radiation and energetic particles would persist for years to decades, altering atmospheric chemistry, creating new compounds, and potentially triggering climate fluctuations. The delicate balance that sustains life could be seriously disrupted. Yet, despite these dramatic consequences, it's worth noting that the universe is vast, and stars like Betelgeuse rarely come this close to Earth. The average distance to massive stars in our galaxy is typically hundreds or thousands of light-years, making a nearby supernova an exceptionally rare event. The scenario underscores why our current vantage point, 640 light-years away, is nearly perfect. We get the spectacle without the threat. Imagining these what-if scenarios also provides perspective on the delicate cosmic balance that allows life to exist. Earth happens to be far enough from massive stars to avoid their destructive radiation, yet close enough to benefit from the heavy elements they distribute after exploding. Carbon, oxygen, iron, and other essential elements in our bodies and on Earth owe their existence to past supernovae, some of which occurred millions of light-years away. Betelgeuse's current distance preserves that balance. We gain the visual and scientific rewards without the physical costs. In essence, these thought experiments illustrate both the raw power of massive stars and the protective role of interstellar distances. They highlight how fragile planetary environments can be in the face of cosmic extremes and why understanding stellar evolution is not just academic, it's a glimpse into the conditions that make life possible. Betelgeuse's eventual supernova promises to be one of the most spectacular events in human history, a cosmic show that could rival anything we've ever witnessed on Earth. Unlike solar eclipses, meteor showers, or even auroras, a supernova of Betelgeuse's magnitude is a once-in-millions-of-years event for our region of the galaxy, and humanity could potentially observe it in real time, from beginning to end. The anticipation is fueled not just by its proximity or brightness, but by the unprecedented opportunity to witness stellar death unfold before our eyes. If Betelgeuse were to explode within our lifetimes, the first signal we would detect might be a flood of neutrinos. These ghostly particles, invisible and nearly massless, would pass through Earth's matter unimpeded, alerting scientists to the core collapse hours before light arrives. The very idea that a cosmic messenger could precede the explosion itself adds a layer of suspense. We would know that history is about to be made even before the sky changes visually. When the light finally reaches Earth, the transformation of the night sky will be staggering. Betelgeuse could outshine the full moon, dominating Orion and casting its glow across the Earth even during daylight hours. Nighttime skies would be bathed in a reddish brilliance, a glowing testament to the power of nuclear fusion and gravity at their most extreme. For weeks or even months, the star that has been a static shoulder of Orion for millennia will become a dynamic, almost living presence in the sky, capturing the attention of people everywhere. The event will be not just a spectacle for astronomers, but a shared cultural experience for humanity, reminiscent of ancient guest stars but on a scale never before seen. The supernova's brilliance will be more than just light. It will be a story written in energy across the cosmos. Scientists and amateurs alike will track the changing intensity, the expansion of the remnant, and the dispersal of material into space. Each observation will provide critical data for understanding the physics of core-collapse supernovae, offering humanity a rare front-row seat to one of the universe's most extreme processes. The anticipation is also emotional and philosophical. Betelgeuse is not just a point of light, it's a symbol of cosmic impermanence. Its impending death forces us to confront the vast scales of time and energy in the universe, reminding us that even stars, seemingly eternal, have life cycles. For those alive to witness it, Betelgeuse's supernova will be a defining moment, a reminder of our smallness in the cosmos, but also of our ability to observe, measure, and understand phenomena that unfold on scales far beyond human lifetimes. This event will also leave a lasting legacy. The nebula created from Betelgeuse's explosion will be visible for thousands of years, a permanent marker in the sky of a cosmic event that occurred during our era. Future generations of astronomers and stargazers will look at that remnant and know that humanity once saw the parent star erupt in unparalleled brilliance. In a sense, Betelgeuse's supernova is a bridge across time, a moment of fleeting visual brilliance that results in millennia of scientific and aesthetic legacy. Even if the exact timing is unpredictable, the mere possibility that it could happen soon adds to the thrill. Every glance at Orion becomes a subtle reminder that the universe is alive, dynamic, and capable of extraordinary events at any moment. The anticipation builds as astronomers monitor its surface, measure its pulsations, and track its mass loss, all while humanity waits for the great cosmic finale. In short, if Betelgeuse explodes in our lifetime, it will not just be an astronomical event, it will be a cultural and scientific phenomenon of unparalleled scale. It will unite observers across the globe in wonder, provide decades of invaluable scientific data, and etch itself permanently into the history of human experience. The star that has long been a static fixture of Orion will become a legend in the sky, a blazing reminder of the immense power, unpredictability, and beauty of the universe. As we reach the conclusion of our exploration of Betelgeuse, it's impossible not to step back and marvel at the sheer scale, power, and beauty of this extraordinary star. Betelgeuse is far more than a bright point in Orion. It is a cosmic storyteller, narrating the life cycle of massive stars, the creation of elements, and the transformative processes that shape galaxies. Its existence reminds us that the universe is not static. It is dynamic, unpredictable, and filled with forces that dwarf human comprehension. Betelgeuse embodies extremes. It is a star thousands of times larger and more massive than the Sun, burning with an intensity that challenges our understanding of energy and matter. It pulses, dims, and sheds vast amounts of material, hinting at the extraordinary physics occurring deep in its core. Eventually, it will end in a supernova explosion, a cosmic event so powerful that it will momentarily outshine the moon and dominate our sky. This is an event that humans, in all our history, have never witnessed up close, a reminder of both the vastness of the universe and the privilege of being alive at a time when such an observation is possible. Yet, Betelgeuse is also a symbol of the delicate balance of cosmic life and safety. While it is massive enough to trigger a supernova, it is far enough away that Earth will emerge unscathed, leaving us free to marvel at the spectacle rather than fear it. The star's death will seed the galaxy with heavy elements, contributing to the cosmic recycling that makes planets, life, and ultimately humans possible. In this sense, Betelgeuse is not just a destroyer but a creator, a stellar force whose life and death continue the ongoing evolution of the universe. Reflecting on Betelgeuse also emphasizes our smallness in the cosmic scale. A single star, 640 light-years away, can dominate the night sky and generate energy beyond comprehension. Yet from our vantage point, it is simply a flickering light, a silent, majestic presence. It is humbling to realize that we are but observers of processes that unfold over millions of years, at scales and energies far beyond our daily experience. And yet, despite this smallness, we are lucky. We have the tools, knowledge, and curiosity to study Betelgeuse, to predict its behavior, and perhaps even to witness its final act. Few species in the universe have the capacity to observe such a cosmic event with understanding and awe. Betelgeuse also inspires philosophical reflection. It reminds us of the impermanence and interconnectedness of all things. Like Betelgeuse, everything in the universe has a life cycle, from the smallest particles to the largest galaxies. Its supernova will not be an isolated incident but part of the grand tapestry of creation and destruction, linking the death of a star to the birth of new stars, planets, and potentially life. Every atom in our bodies, every element on Earth, was once forged in the cores of stars like Betelgeuse, making us literally children of stellar explosions. Finally, the anticipation, mystery, and majesty of Betelgeuse underscore the human drive to explore and understand. Our telescopes, neutrino detectors, and observatories allow us to peer into its secrets, track its changes, and prepare for its inevitable supernova. Through Betelgeuse, we confront both the limits of our knowledge and the heights of our curiosity. It is a reminder that the universe is not just a backdrop to our lives but a dynamic participant, full of lessons, surprises, and moments of awe. In conclusion, Betelgeuse is a cosmic beacon, a star whose life and impending death teach us about the power of nature, the beauty of the cosmos, and the interconnectedness of all matter. It demonstrates that even in the vast, cold expanse of space, there are forces of immense energy and creativity, shaping the universe on scales we can scarcely imagine. And as we gaze upon Orion, knowing that this colossal star is approaching the end of its life, we are reminded of how small yet fortunate we are, privileged to witness, understand, and be inspired by the grandeur of the cosmos. Betelgeuse is not just a star, it is a story of life, death, and rebirth on a scale that transcends human experience, a luminous testament to the extraordinary universe we are part of. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. If you enjoyed the video, consider subscribing to the channel and like the video.